Good morning. Hello, everyone.
Morning.
Morning.
Well, it might be. I should say greetings from Miami because it could be good afternoon in other places. We have a participant from Cape Town, so I think we may be covering a wider set of time zones for this meeting. Hey, Jeff, how are you?
Good morning, Julio.
Nice background.
That's Mesa Canyon in Canyonlands National Park.
Beautiful.
Mesa Arch.
Very nice. So I see we have so far 15 participants. I know we had a healthier registration. Let's see, Basi, what was the registration number at?
52.
52. Wow. Okay. So let's give it maybe a few more minutes for people to join, and we'll get started. Hello, Alex.
Hi, Julio. How you doing?
How are you? Good, and you?
We're
How's Rio? How are things in Rio?
Rio as well. It's raining today, but very hot, and we are struggling with our pandemic out of control around here. But we are doing fine here. We are okay.
Good. Great to see you.
Great to see you too. Hi, Basi.
Let's see. So we're up to still at 15. Okay. Well, we'll get started soon.
With that many, maybe we should start introductions. Are we going to do all around or?
I was thinking that we wouldn't have time because we had such a healthy registration, but with 15 people, I think we could. So I'll go ahead.
15 and let people say something as they come on.
Okay. So you start first, Jeff.
All right. So I'm Jeff Cantor, long time with the SAACC and 17 years with Rubin Observatory, and most recently helping out on some other initiatives, notably the U.S. Extremely Large Telescope Program. And this is my final co-chair of the SAACC with Julio. I'll be asking someone else to step in, and we already have a person who's agreed, and that's Bob Blum.
Great. I'll go next. I'm Julio Ibarra, principal investigator of the AmLite project, and also co-chair of the SAACC with Jeff. Who would like to go next? Vasi, you want to go next? You're next one on my screen.
Hello, good morning. My name is Vasilka Shergarova. I'm a research coordinator for Sierra here at Florida International University.
Christian?
Yeah. Hi, my name is Christian Silva. I am the IT manager of Rubin La Serena. And this is my second SAACC meeting for Rubin.
Okay, Alex?
Hi, I'm Alex Morat, Brazilian and RMP, and I'm the science engagement specialist.
Okay. Mike Nolta?
Hi, I'm Mike Nolta. I'm part of the CCAT East project, and I'm in Toronto.
Okay, welcome, Mike. Bob Blum?
Morning, everybody, or afternoon, evening, wherever you are. My name is Bob Blum. I'm the acting Observatory Operations Director, part of NSF's Noir Lab.
Great. Ed Ajar?
Hi, Ed Ajar. I'm the Program Officer at NSF for the Rubin Observatory.
Okay. Mauricio?
Good morning.
I'm Mauricio Villiers. I'm with CBS4, and I'm the cost account manager for Chile site integration and commissioning.
Thank you. Let's see, Mauricio Rojas.
Hi, good morning, everybody. Mauricio Rojas, Network Engineer, NOIR Lab.
Thank you. Tiago Monsores.
Hello, this is Thiago.
Thank you, Tiago. Okay, Giorgio Philippi or Philippi.
Felipe, hi.
Hey, Giorgio.
Hi there.
Good to see you.
Good to see you too. Good to see everybody.
Okay. You wanna say who you are? Yeah, you. Yeah, say where you're. A little bit about yourself.
Yeah, Giorgio Filippi from the European Southern Observatory. I'm here more as an observer than not directly involved in the SAACC, but I've been to the SAACC since long. I was involved in various communication projects for both ALMA and ESO, and that's why I'm connected to this world of communication.
All right, thank you. Mauricio Rojas.
Yes, sir. Good morning, Mauricio Rojas, Network Engineer from NOIR
Oh,
Lab.
we got you.
Yes,
okay,
sir.
perfect. Okay, Albert Astudillo.
Hello everyone, Albert Astudillo here, CTO of Riuna in Chile.
Thank you, Albert. Luis Cadenas.
Hi, Julio. Hi, everybody. Luis Cadenas, CEO of Red Clara.
Right, perfect. Adele Plunkett.
Everyone, Adele Plunkett here. I'm from NRAO in Charlottesville, and we'll be reporting on ALMA with my colleague David Halstead. I'm an astronomer for NRAO.
Okay, thank you. David Halstead.
Yes, hi indeed. David Halstead, Chief Information Officer for NRAO and representing the North American ALMA Science Center.
Okay. See Chris Griffin.
Yep, Chris Griffin, Chief Network Architect for Florida Lambda Rail.
Hey, Chris.
Hey.
Eli Dart. We'll move on. Heidi Morgan.
Sorry, I'm trying to find the mute button. Eli Dart, ESNet. Good to see you all.
Good to see you, Eli. Heidi Morgan.
Good morning, everybody. It's great to see you back at the SAACC, or if you're first-time members, welcome. I'm co-PI of AmLite, and been here since the beginning, and it's still great to be here.
Thank you. Italo.
Hi, good morning, everyone. This is Italo from AmLite Sierra, FIU. I work as a network engineer and somehow helping the LSST project.
Great. Welcome, Italo.
Thank you.
Geronimo.
Good morning, everyone. Geronimo Bezerra from Florida International University. I'm AmLite Chief Network Engineer.
Thank you, Geronimo. Let's see. João Eduardo Ferreira, Jeff.
Yeah. Good morning, everyone. I'm João Eduardo Ferreira. I am the new coordination of all the ANSP and the new Research and Education Network at São Paulo, or HEDNASP. Pleased to stay here for the first time.
Welcome, Jeff. Let's see. Jorge Ibsen.
Hi, my name is Jorge Ibsen. I am the head of computing in ALMA in Chile. I work closely with Adele and David with respect to ALMA data transfer.
Welcome, Jorge. Julian Borrell.
Hi there, I'm Julian Borrell from Berkeley Lab in UC Berkeley. I'm the co-spokesperson of CMBS4. I'm the project data scientist for CMBS4, and I'm also an L3 for Simon's Observatory and have worked on polar bears, so many generations of Chilean experiment. This is my first time at SAACC. Thank you very much for the invitation.
Welcome, Julian. Julio Costanzo.
Hi, everyone. Morning. I'm Julio Constanzo, IT network engineer from Rubin Observatory.
Welcome, Julio. Kevin Thompson.
Good morning, Julio. Kevin Thompson, Program Officer at NSF.
Welcome, Kevin. Let's see, the list is getting longer. Let's see, we have Paola Arellano.
Hola, hi everyone.
Okay, let's see, Nigel Sharp. Saw Nigel here, yes.
Yep, Nigel Sharp from the National Science Foundation. I am kibitzing on this. I have my fingers in a great many different projects here, a little bit of a finger in a great many projects at NSF.
Wonderful,
Hi,
welcome, Nigel. Let's see, Paul Weffel.
Hello, everyone. I'm Paul Wafel. I'm a network engineer with ESNet, the Department of Energy Science Network, working on the Vera-C Rubin Observatory project.
Welcome, Paul.
Thank you.
Phil DeMar.
Phil DeMar, Fermilab, contributing to the VRO net activities.
Good to see you, Phil. See, Renata Frez.
Hello, I'm a network engineer in the RMP, and I'm working with the project, the AMLIGHT project.
Welcome, Renata. Rob Salina.
Hi, Rob Salina with NRAO. I'm the NGVLA project engineer.
Welcome, Rob. Welcome. Let's see, Sergio Cofre.
Hello, I am Sergio Cofre, and I'm network engineer of Rona.
Welcome, Sergio. Shukri Wiener.
Hi there, everyone. Shukri Wiener from TNET. I'm the Executive Officer for Technical and Operations.
Welcome, welcome, Shukri. And let's see, we have Simone.
Hi,
from
Simone.
Simons.
Yeah, Simone Ayala.
Good to see you again.
Good to see you too. Simone Ayala from the CCA in New York City. I lead the data management for the Simmons Observatory, and I'm part of the Atacama Cosmology Telescope.
Great. Okay, Sam Chan.
Morning, Sam Chan, IT Director and Information Security Officer for GMTO.
Okay, and Tiago.
Yes, I'm the network engineer for the Clara project.
Okay, wonderful. If I missed anybody, the floor is open. Go ahead and introduce yourself.
I'm Eduardo Toro, Information Technology Engineer from NoirLab IT Ops.
Hi, Eduardo.
So
Anyone else?
Yes, I'm Nadine Neroud. Do you hear me? Do you hear me?
Okay, welcome.
Hi everyone, Nicolás Obando, Network Specialist in Alma, Chile.
Welcome, Nicolás. Okay,
Gisela
anyone
Capus
else?
From, yes, Gisela Capus from ESNet.
Hi, Gisela, welcome.
Christian Saldias from Alma, IT Manager.
Okay, wonderful.
Nadine Neroud, representing CTA Observatory.
Okay, wonderful. Welcome. Okay, if that's it, why don't we go ahead and get started with the meeting. I will share my screen and do an introduction, a quick introduction about the SAACC meeting. You know what the SAACC is, basically, and why we're here. Okay. Oops, pressed the wrong button again. All right, so my name is Julio Ibarra. I'm the principal investigator for the AMLIGHT project based here at Florida International University in Miami. And the SAACC means the South American Astronomy Coordination Committee. For those of you who are new here, the SAACC is a committee that is now in its 10th year. And as Jeff mentioned in his introduction, he's co-chair of the SAACC. Actually, he's chair of the SAACC, and he's with the Vera Rubin Observatory. And we've been working together for quite a few years in having the meeting annually, and it's been very helpful in being able to inform the AMLIGHT project as well as the science projects of activities going on with the development of the network and what we're doing to support the science project. So as you could tell from the introduction, the SAACC is comprised of representatives of the different astronomy projects that are based in South America, and also of the operators that manage the research and education networks in South America and in the US, and also in Africa. And we work together as a community to support each other's requirements, and primarily to improve the data movements of the science projects between South America and the US. The goals of the SAACC primarily are to provide input and advice to me as the principal investigator and our project team on the programmatic needs of the science projects, and to also provide a venue that we can meet and coordinate among the needs of the different projects. So one of the things that is important is how we can work together, in particular how the research and education networks can better support the science projects. So it's really important that we inform the science projects of the roles of the research and education networks in being able to assist you with the movement of data between the distant facilities there in South America and to the users in the continental US. During our meeting today and tomorrow, you will hear about new technologies that we will be deploying on the AMLIGHT network to improve the exchange of data across these wide geographies. We have a little bit about the AMLIGHT network itself. So the AMLIGHT network interconnects the United States to key aggregation points in South and Central America, and now also Africa. These points are in Brazil, Chile, Panama City, and in Cape Town. This year, we actually have a new 5-year award from the National Science Foundation. Last year, I mentioned that we had submitted our proposal, but I now inform you with good news that we have a new 5-year project, and this is a project at FIU with also University of Southern California, ISI, and Vanderbilt University. And AMLIGHT is a collaborative and a cooperative partnership among the research and education networks in South America and Africa. We have representations here from Red Nest, formerly known as ANSPI, RMP, Red Clara, Reuna, Aura, the Vera Rubin Observatory, Florida Lambda Rail, and Internet 2. And we really couldn't do this without the support of all of our partners in the region. You all should have received a link or an email to the participant guide, and this participant guide provides you with links to all the materials that you will need for the meeting. If you didn't receive this this email with the link to the guide, please let us know in the chat, and we will provide that for you. Presentations today are a duration of 15 minutes plus 5 minutes for Q&A. If there are any questions during presentations, please provide them in the chat, and we will respond either during the presentation or at the Q&A period. There's also going to be time after today's presentations for further discussion on any questions that people have. So we will be keeping track of the time. So please be mindful of your time limit so that we can stay on time today with the agenda. I would like to thank the program committee, which is Jeff Cantor, Vasilka Chegarova, and Heidi Morgan. We've put together a nice program, I think, for you for updates of all the projects and the networks in the involved with the AmLite project. And I want to give a special thanks to Vasilka for helping with the coordination, the logistics, and many details that have organized the agenda for today. So with that, we can go ahead and get started with the presentations of the science projects, which is what we'll cover today. And tomorrow we will have the updates from the network operators. So I'm going to stop sharing my screen. And let's see, who is the first presenter? Is it Jeff and Christian, I think?
Yeah, so we're going to cover two projects, Vera Rubin construction and the USELT program. Christian is going to cover the first part of that. So I'll jump in at the end. So Christian, it's all yours.
There you go. Couldn't find my mute button. All right, can you see my screen?
We see you, but not in presentation mode. We see you in just.
That's fine. What about now?
Yep.
Looks good.
All right, great. Thank you. Right. Good morning, everybody. My name is Christian Silva. As I mentioned, I am the IT manager of Rubin Observatory here in La Serena. And I'm going to talk a little bit about the network operations here in Rubin. So first, I'm going to cover just a big picture so you get an idea of how everything works here in Chile. Then I'm going to talk a little bit about the internal components of the network, some of the 2020 events, and I'm going to leave some time for questions at the end of the presentation. Right. All right. So this is the big picture of everything that happens in Rubin in La Serena. Once the data it's acquired by the camera, the summit sends the data to the base. Right. We have special links between summit and base to do that, and we have many links. So we have a 40 by 10 gigs link, which is exclusive for science data, and we also have a 2 by 100 gigs link, which is for control data. This is, for configurations and transfer of data between summit and base that is not necessarily related to science. Those two links, they belong to Rubin, and they were provided by Reuna. They use DWDM technology. There's also a third link, which is a 10 by 10 gigs link that belongs to Aura, and it's a shared link. This is for all the programs at the summit. They can use this link. Right now we're using about 20 gigs of that, right? But the two important links for us are the 40 by 10 and the 2 by 100. There's also a fourth link with enabled not long ago, which is a backup link, but it's not really a backup as per se. It's mostly a survival link. We acknowledge that there could be some problems between the link between summit and base, so we can still reach the summit from the base using this survival link. There's a jump in the middle that goes to Tololo, then jumps to Pachon, but this is the idea, right? This all microwave link. This is very low bandwidth, so we only use it to reach the servers and the network equipment to verify that everything is good at the summit. So once the data arrives to the base, the data can have two destinations. They could go to the internet, right? And for that, they use the Aura border router with their link. Or it could go to the USDF. And if it goes to the USDF, they go using the Rubin border router, 1 or 2, and they enter the long-haul network, which is this big network with all the our colleagues of different providers along the path. So we have a primary link to the long-haul network of 100 gigs, which is working right now. And a few days ago, we were just able to finish the physical installation of the backup link, which is a 40 gig link on a 100 gig link, but we only use 40 there. And they both use different paths to reach to Santiago. The 100 gig goes to the valley and the 40 gigs goes to the coast. It's actually going on Route 5, which is the road from La Serena to Santiago, right? But as I said, the 40 is not yet enabled. It's just been installed, right? So after it reaches Santiago, it goes to the long-haul network, yeah, and gets to the USDF. This is the big picture of the data for Rubin, right? These are some of the internal components of our network, right? And the base and summit are very similar. So for the production environment, we have lots of Kubernetes and containers and some physical servers. We don't have many virtual machines, right? So our approach here is just they're all working inside a Cisco ACI technology, which is an SDN product from Cisco. However, in the user side, we do have a classic NXOS, right? And we do have more VMs, also Kubernetes and physical servers, right? So the users is a typical, telephones, users traffic, right? And we also have a special environment just for the base, is for the long-haul network. And we have the 2 border routers that I just mentioned, and physical servers like the DTN and the perf sonar that are used to measure the bandwidth and the quality of the bandwidth of the long-haul network. We're also leveraging some of the cloud services in Google and Amazon. We have some services being launched there. So, so this is a very high view of the internal components that are happening in the Rubin network, right? They're both very similar, Summit and base, but we only difference of the long-haul network to base. So I'm going to talk now about some of the events that happened last year, some of the important events that could be of interest. So in June of 2020, Jeff organized the network pre-verification review, right, for the long-haul network. And one of the topics of the long-haul of that review was to review if the Cisco ACI technology in our network was good. I mean, if we need to be reviewed again. So the panel during that review said that we should have another review of the Cisco ACI and find out if it's a good fit for us. And this is based on complexity concerns and our certainty about the benefits. So in September of last year, we organized a local network review with several colleagues that are also in this meeting, like Albert from Reuna and Nicolas Obando from Alma. So they help us to find out if the Cisco ACI was a good fit for us, and based on their recommendations, and also with the same concerns about complexity, sizing, and other factors, they recommended we should migrate our production environment from Cisco ACI to NXOS. We took the recommendation, and we are in the final steps of the planning of this migration. Also last year, we installed several new servers at the base on Summit, new clusters. ComCam, the commissioning camera servers were installed twice. One is the base, one on the Summits. The LSST-CAM servers were also installed at the Summit. Several clusters serving a lot of services are being deployed last year. We announced the selection of the Google as an interim data facilities for Rubin. The idea of this is to we can learn the system and processes that are being developed by DM, and it will serve also as a data preview scenario, right? This is all followed by the Google proof of concept that was done during the year. This is the document DMTN 157 that could be found on internet, it's publicly available. We also selected SLAACC as our USDF. So that means there's a new path to the USDF for the long haul network. We're working on that with the net members. And finally, what probably the most important event for all of us for the pandemic, right? So we have many things happening because of that. We have to power off and power on the summits during the year. We learned that we can power off everything in one day and power on back in a couple of weeks. And we also took the time to increase our documentation. We did lots and lots of documentation on the network and the infrastructure in Rubin. So it was a good opportunity for us and a good use of time. All right, so this is a brief summary of the network operations. Are there any questions?
I have a question, Christian. Eduardo Duro from. Hi. You mentioned that in the Rubin have more Kubernetes architecture rather than to use virtual machines. What is the reason of that? It was just a few machines virtualized?
One of the things that are important for us is the automation, right, and the velocity of things and the scalability. So the Kubernetes provide us all those aspects to the operations. We can quickly escalate if we need to get more power computing, and we can also automate all our deployments. I mean, you can do that eventually in VMs, but in Kubernetes it's much more easier. Also, the good thing about Kubernetes is that if you know that your configuration works on one computer, you know it's going to work in another computer. So this is one of the concepts that we're using for the IDF. We know that everything that we're going to do in the IDF is going to work in the USDF because it's based on Kubernetes.
Okay, thank you.
Welcome.
Okay, if we've covered the Rubin, I'll just make a quick parenthetical remark about the U.S. Extremely Large Telescope program before Bob picks up with Rubin operations. So I'm going to share my screen very briefly. So this is the homepage at NOIR Lab for the U.S. Extremely Large Telescope program. This is a joint endeavor between NOIR Lab, the 30-meter telescope, and the GMT. And the goal of the program is to secure funding for both GMT and TMT to complete the telescopes and make available to the U.S. astronomy community 25%, or at least 25% of the observing time available on those telescopes. We would develop a strong key science program for the community or with the community. In particular, where we see this of particular value is when a key science program might need to take advantage of the different capabilities of both the GMT and TMT. We'll also have smaller scale discovery science programs associated with that. So NOIR Lab's role in this, obviously we have two world-class, very extremely large telescopes in the mix, but what does NOIR Lab do in that? Well, we provide user services, documentation and training to support the entire research lifecycle. So that's from submission of proposals and time allocation evaluation up through observation, planning and preparation, and then tracking along with the observations, and retrieving data and archiving that and making it available on a long-term basis. So this program is in the proposal stage. We have submitted to the 2020 Decadal Survey. We're waiting for the report out of that to determine if we can take the next steps into design. There have been a couple of awards already for research and early program development type activities. And we're hoping to submit a full-scale major research and education facilities construction proposal to the NSF, assuming a good recommendation from the Decadal Survey. Networking-wise, TMT is currently baseline to be in Hawaii. We expect it will be there, irrespective of the cultural obstacles that there are currently. And then we have GMT in Chile. So we expect to configure order of 10 to 20 gigabit per second links between those two observatory locations and NUAR Lab in Tucson. And that is part of the proposal that we envision. So at some point, we hope USELT will be a bona fide member of the SAACC and will be participating in much the same way as the rest. Okay, and then my last comment, I mentioned before that I had been a long time involved with the SAACC and for part of that time co-chairing. So this is the before picture. And of course, this is now. So there's been a bit of a change.
You look the same, Jeff.
I'm looking forward to handing the baton off to Bob Blum. And with that, I'll ask Bob to give his presentation.
Thanks, Jeff. It's clearly still Jeff, maybe a little grayer and a little wiser, but thanks for everything you've done, both for Ruben, USELTP, and the SAACC, of course. I'm just going to bring up the slides here. Okay, so thanks. I am Bob Blum. I am at NUAR Lab and currently working with the nascent operations team to get Vera Rubin operations plan and team ready for operations when it commences in a few years. Just wanted to start off with a few brief notes about some changes. It seems like a long time since we've been together and a lot's happened. And with the COVID year in between, there's something about COVID time that it makes it seem like, you know, there's no, it doesn't exist or something, I don't know. But anyways, it seems like a long time since we've been together. So just to bring you up to speed, we are very happy to have a new name, the Vera C. Rubin Observatory, and we've made a new logo and we have a new look, and we're just really happy to move ahead in this new way. We will keep the LSST acronym. It used to mean Large Synoptic Survey Telescope. It now means the Legacy Survey of Space and Time. So that's the thing that the Vera C. Rubin Observatory will execute over time. We're extremely proud to be named after Vera C. Rubin, a really important and groundbreaking scientist for much of the last 50, 60 years. And the first facility, national facility in the US named after a woman scientist. So we're extremely proud of that. We do ask you to be sure to honor Vera by using her name. So we like the short form of Rubin Observatory rather than making it initials. So we'd like you to please keep that in mind. This logo, I won't go through all the details here, but it's actually quite interesting, and the team did a really great job of designing it. There's lots in here. There's diversity, there's discovery, there's new ideas. There's even the connection from taking photons and going into big data through the electronic traces on electronic readout boards in the campus. So take a look at that and see what great work our design team did on our new logo. Okay, it has indeed been a really interesting year. As for everyone else in the world, the COVID-19 pandemic had a major impact on the Vera C. Rubin construction project and on our operations planning. We turned out that we stopped construction activity last March, a little more than a year ago, and we're still not quite back to full steam yet. We are ramping up activities in Chile, and I'll show you a few slides of the evidence of that, but it's still a little bit slow going. We're not quite out of the COVID woods yet because there's still a surge of cases happening in Chile right now. But I think we do hope and see that, like the rest of you, the light at the end of the tunnel. And so we're just making progress and plans to keep moving, and we will get there. The work at SAACC in California also had to be greatly reduced last year. They are back to integrating the camera, and I'll show you some of the great progress that we've made despite the pandemic there as well. But first, for those who may not have a great sense of what Vera Rubin Observatory and the LSST will be all about, I'll give you this really quick update or brief summary of what we're going to do. It's really unprecedented astronomical survey in the optical wavelengths. We cover the southern sky every 3 nights, the entire southern sky, and we do that over and over again for 10 years. We will have, at the end of that, about a 40 billion object catalog with trillions of source measurements for those 40 billion objects. We're going to take 20 terabytes of data per night. So that's the reason that you saw this very large and capable network that AmLight is helping us put together, and the other partners are going to do, so we can get that data from the telescope in real time every night to our processing facility in California. We will have 10 million transient alerts, and so we need to process that data within 60 seconds and alert to the astronomical community what's happening in the night sky in real time. That's another reason for this very large, highly capable wide bandwidth. We have annual data releases, and we will end up with a 15 petabyte final catalog and 500 petabytes of image data products. Our data releases will be proprietary for 2 years, and then we will make them public. We haven't got all the details on the public data release down yet, but we're working on it, and we expect to have that set up before operation starts. So the current first light and survey schedule has slipped out due to COVID. We are expecting right now on our current plan to have a first light of about November of 2022, engineering first light with our so-called commissioning camera, and then have the full camera have first light early in 2023. We are planning as an operations team not to start earlier for the full survey than October 1st, 2023, and that date is still somewhat uncertain. As I said, we are still dealing with COVID and the follow-on impacts from that. In any case, once we get going, we'll go for 10 years and we'll finish sometime early in the 2030s. These images show some of the great progress we've made despite the pandemic. So the telescope is taking shape on the mountain in Cerro Pachón in Chile, and the camera has its full focal plane, which has been tested at least in part, and it looks very good. And those science CCDs are all inside the doer and looking good. That's actually an image of Vera C. Rubin taken with a pinhole projector with the full focal plane. Just to give you a quick sense of what's happening on the mountain, I couldn't resist showing you this video. I won't play the whole thing, but we have started back on the mountain very carefully with COVID protocols in place since about November of last year. And we're just getting to the point where we're going to get the telescope really going in the rest of this year. That's kind of the key pacing item now to get this done, is to finish the telescope, get it all working, get the optics in there. All the optics are there on Cerro Pachón, and it's a matter of just integrating and testing. We're still not quite there with the COVID travel restrictions. We have teams that can't quite get to the mountain yet, but they hopefully will be there soon. So this shows just a few weeks ago, the top end, the final big part of the telescope structure itself being put in on the mountain in Chile. And in the next months, we'll start actually finishing the testing of this system with surrogate mirrors, and then we'll move on toward actually putting the commissioned camera on. You can take a full look at that video at your leisure. So the camera's making great progress as well. It's in final integration in California. This is a picture of one of the 6 filters. I think it's the R-band filter that was delivered to SAACC and will be installed in the camera. 3 of the other filters are in their final process of being put into their filter holders at Livermore and will be delivered to SAACC soon, and a couple are still being coated. When all the filters are done, that will be the last major aspect of the camera that needs to be delivered to SAACC, and it can be integrated fully in the next year and then sent to Chile to await installation on the telescope itself. So we're making great progress. Operations is also making progress. We are actually in operations now, what we call pre-operations. It's mostly operations planning, but we're starting to engage with the community, and we're going to have a data preview of simulated data come out and served on our science platform this year. We also are making progress on the final strategy for the survey, what we call the cadence studies, and we are working on our in-kind program for international participation. So our planning for operations of the survey is in full swing. We have a full survey proposal and detailed plan for operations that will go in this year. So you can check with us at the AAS next January and see how we did. I expect that we'll do good. The team is ramping up this year. We have 100 people with 40 FTE from the WAR Lab and SAACC and our affiliates and associates, including UW, Princeton, NCSA, and other DOE labs. And we are now planning to do a data preview for the community this spring and summer. And what does that mean? We are going to host about 300 what we call delegates who will be chosen from the data rights holders in Rubin Observatory to participate in using a simulated data set produced by the Dark Energy Science Collaboration and deployed on our Rubin Science platform in the Google Cloud, our so-called IDF that Christian mentioned. That's going to happen in June. The team is actively setting that up at Google right now, and it's going quite well. So we're really excited to see this happen. So real Rubin-like data for people to prepare working in the science platform to understand what the data might look like and how their science programs could be developed for the full survey. And we've had multiple community-based information sessions on that, both at the last AAS and then separate ones hosted by our community engagement team. Just a few words then, I'll wrap up about the survey cadence. This is a big thing that we're working on right now to get settled. What is the actual survey strategy? What is the cadence of observations nightly and yearly and then over the 10 years? We have a baseline strategy, and we're reviewing that right now with input from the community, so-called community-based cadence science notes, basically the different science collaborations telling us what the optimal cadence they would like to do. And we will balance those inputs, which speak to the 4 science pillars, the different science cases that are all designed to be executed by the Legacy Survey of Space and Time, and we'll pick the best cadence that does the most science for all those different science areas. So that's actually going on right now, and we expect by the end of this calendar year to have a good idea of what an initial cadence will look like, and then we'll continue to refine that over the intervening period before we start the survey. So cadence means how often we visit fields every night and in between nights. We have a wide, fast, deep main survey that basically covers the sky. And then we have other things like so-called deep drilling fields that stare in a certain position over and over again. And they are designed to do different types of science. We are accepting those cadence notes right now till April 15th, and then our survey cadence optimization committee is going to work on those and come back later this year with an initial strategy. So I think that's the end, and I will take questions if there are any, but thank you very much for listening to this brief update from VRC Rubin Observatory.
Thank you, Bob. Any questions for Bob? Beautiful photos, beautiful video.
It's amazing the progress the team has been able to make even despite the COVID. So it's almost full steam ahead soon.
Wonderful, wonderful, very exciting. All right, let's see, who do we have next on the agenda? We have Noir Lab, Eduardo Toro and Mauricio Rojas.
Good morning, everybody. Let me share my screen. Here we go. Just a second, please. Okay, here we go. Can you see the presentation, right?
Yes.
Okay, good morning, everybody. Welcome to NOIR Lab IT Ops presentation. This presentation will talk about NOIR Lab, IT Ops, backbone networks, MSO and Gemini South integration, main activities during the 2020, and the future activities for the IT Ops groups. NSF NOIR Lab, formerly named the National Optical Infrared Astronomy Research Laboratory, unifies all of NSF nighttime optical infrared astronomy facilities in a new organization. The mission of the lab is to enable breakthrough discoveries in astrophysics by developing and operating a state-of-the-art ground-based observatories and providing data products and services for a diverse and inclusive community. Through these 5 programs, CTIO, Cerro Tololo Inter-American Observatory, CSDC Community Science and Data Center, Gemini Observatory, KPNO Kitt Peak National Observatory, and the Vera Rubin Observatory, NOIR Lab serves as a focal point for community development of innovative scientific programs, the exchange of ideas, and creative development. AURA, the Association of Universities for Research in Astronomy, operates these facilities and NFS NOIR Lab and in a cooperative agreement with the National Science Foundation. IT Ops infrastructure and operation support standardized systems deployment and management, as well as IT support requirements reaching all levels of NOIR Lab. This includes astronomy IT operations, business IT operations, NOIR Lab business and services areas. The first primary area of responsibility of IT Ops is business IT operations. This one delivers and supports integrated IT services across all NOIR Lab sites, provides the IT services necessary to run the business of a modern and globally distributed organization. Services include our provisioning and administering end-user system, networking, internet connectivity, centralized account management and authentication services, data storage, integrating cloud services and cybersecurity. The second primary area of responsibility of NOIRLab is the astronomy IT operations. This one delivers and support enterprise computing services dedicated to support the science. This includes scientific data collection, scientific data storage, data access, data movement, a standardized system configuration of device, and system monitoring. And it's very important to mention 23 members of the staff are distributed across all NOIRLab sites in Chile, Hawaii, and Tucson. NOIRLab serves two different kinds of tenants, the larger and the smaller. In the larger group, we have Gemini, MSO, Blanco, SOAR, and SOAR, Rubin Observatories in construction, Las Campanas Observatory, NRAO in Santiago, and the smaller tenants are the Smart Group, Prompt, Gong, ALO, LCOGT, WOM, CASI, ASASSN, Everyscope, Emerth, and T80. To give the service, the primary link from Chile to US provides 10 gigabits per second versatile to 40 gigabits per second running along the Pacific coast, the orange line on the slide on the left. And 10 gigabits per second versatile to 40 gigabits per second backup link runs along the Atlantic coast, the yellow line. In case of failure of both links at the same time, Reuna kindly provide a shared 10 gigabits per second connection through Red Clara. From La Serena to Santiago, a fiber link that runs through the internal valleys, it was mentioned by Christian a couple of minutes ago, provides the primary circuit of 40 gigabits per second, the red line on the diagram. On the other hand, we have a fiber link that runs parallel to the Pan American Highway. The Route 5 North provides 4 gigabits per second backup link, the yellow link on the diagram. The connectivity from the mountains to La Serena, all the tenants share 20 per 10 gigabits per second link from Cerro Bachon and Cerro Tololo to La Serena, provided with a fiber using this wavelength division multiplexing, DWDM. In case of failure, the primary link circuit for the infrastructure is provided by a 400 megabits per second microwave link from La Serena to Cerro Tololo, and 300 megabits per second microwave link from Cerro Tololo to Cerro Bachon. A secondary backup link from La Serena to Cerro Tololo via 300 megabits per second, and a link from Cerro Tololo to Cerro Bachon provide an additional 200 megabits per second between the summits in case we need it. Gemini has an exclusive backup link by 300 megabits per second from La Serena to Cerro Bachon. Okay, now we are going to continue this presentation. Eduardo will give details of the transition process and the jobs done during 2020. Eduardo?
Hello, everybody. Thank you, Mauricio. I will start this presentation talking about the International Gemini Observatory. As the Gemini's motto said, there's one observatory, two telescopes. As usual, the Gemini telescope are still in continued upgrade of networking process. We have Gemini North in Mauna Kea, Gemini South in Cerro Bachon. That probably everybody knows that. During the last couple of years, we are not changing about the Gemini partners. It's United States, Canada, Chile, Brazil, Argentina, and South Korea. Is basically one of the programs of the NOIRLab that is placed in the south. So we want to talk about the Gemini and data centers. Let me see, I have control. Let me move to the next. Okay. Gemini data centers and key uses cases of the networking point of view. Since we have 2 telescopes, we have 4 data centers. 2 of them are places at the sea levels. In the first one is a Hilo-based facility, and the second one, La Serena-based facility. And another 2 are in the mountains. So Mauna Kea operation at 4,200 meters of altitude, and Cerro Bachon operations at 2,700 meters of altitude. What is basically the from the networking point of view, the use cases. We support essentially the base facilities operations. That means the working, the user, external user can do the remote observing, and also the local users can do remote observing from the base, in this case, La Serena base facilities, to Cerro Pachón. We need to provide that VPN access and all the infrastructure related in order to this remote observing can be successful from everywhere. Another important aspect is the key use case is the summit-based data transfer. Right now, we have a high bandwidth between La Serena and Cerro Pachón. Keep in mind that during the last years, we have an upgrade of the DWDM fiber optic connectivity to the agreement with Reuna, and also because Vera Rubin is in Chile, that we have, and we are taking opportunity from Gemini Observatory to have a much better bandwidth, even much better bandwidth that we need, indeed. But it is interesting that it's absolutely one of the requirements very well done during the last years as upgrade. Another two aspects is the high availability and high reliability that permits to the Gemini Observatory to work in a world-class availability. It's more than the 99% between the base and the summit. Even the COVID-19 contingency, we have all the data centers up and running. We never turn off the data center on Cerro Pachón, at least, because there are many instruments and many elements to monitoring remotely. But the observatory was shut down, but the data center was all the time up and running. In terms of the high reliability, the MTF parameters, median time before to failure, we are expecting not pass more than 10 years before to do the upgrade. Right now, we are reaching the 8 years of the continuous operations with the equipment that we modify or we change or replace in 2013. So we are expecting that 2021 could be a good year in order to planning the network upgrade and also planning in the context of the Node lab, which is more important than before. Another element is the cross-site coordination. So all the time we need low latency between Hilo, Hawaii, and La Serena, as well as La Serena and Tucson. That is very important because we are sharing network services between the two sites or the different sites that permit the functionality as one entity. So the VPN site to site is one of that examples. Regarding with the cloud data archiving, the up and download from Amazon Web Services is one of the key elements to Gemini Observatory in terms to have online the data that from the scientific departments or equipment or team, it's important to have available. Okay, we did during the 2020 more updates, even the COVID-19 contingency. However, in our terms of during the last years, I would like to mention that we integrate part of the Gemini infrastructure with the MCO, with basically CTIO in La Serena, using the base data centers. And the left hand, you have the La Serena base facilities, which correspond to Gemini building, basically, or data centers in Gemini building. And the right hand, you have the Cerro Pachón operations. If you see in terms of the networking, is basically the same topology, but it's one of the important things that this diagram represents is because we could satisfy all the use cases mentioned before, but during the 2020, we consolidate the high level diagram, the connectivity from the new firewalls and a modality of failover. And also we incorporate many functionalities in cybersecurity because these couple devices also not doing necessarily firewall, is doing intrusion prevention, anti-malware, URL filtering as a VPN server, and also monitoring for the external connectivity. In terms of the network topology, we still maintain the multi-tier collapsed core and also using access layers to connection of the end users' devices. We have a lot of virtual machines in Gemini right now. Many of them permit us administering even the firewalls. We have a firepower management center. We have active domain controllers. We have identity service engine as authentication servers. We have logs, we have monitoring, and also the DNS physical and virtualized. We connect the base and the mountain, who I mentioned before, using the Ford circuit of 10 gigabits. And additionally to that, we are using an exclusive Gemini Telconor microwave link in order to provide backup in case of failure of the DWDM. One important change during the 2020 is basically we eliminate the firewalls on the mountain. So we control the traffic to the mountain through La Serena. Right now, we don't have firewalls how we did or we have in the past, but we maintain the similar topology. So we have the virtual switching system creating a virtual switch and a lot of port channels between the different components of the network. I would like to mention that during the 2020, we also integrate some functionalities with Vera Rubin that started in 2019, I think. But it's especially now we are more close in terms to provide some coordinated Wi-Fi connectivity on list. Well, in summary, the Gemini saw the improvements during the 2020 is the next generation firewalls, who I mentioned. We increased the number of the tunnel profiles in order to provide access to remote users in Gemini South and Gemini North. Overall, the instrumentation, the visitor instrumentation, which is really important for us. The implementation of URL filtering, even we increase the number of URL license. We also we are participating in the Research SOC initiative, which is an initiative of cybersecurity sponsored by National Science Foundation and Indiana University. If you want to know more details about that initiative, you can see in that link. We move the traffic control to observation operations in order to control to filter in all the access in La Serena, avoiding to use firewalls on the mountain, who I mentioned before. But in this special year, 2020, we have a lot of network services and collaborative tools that the IT Ops is integrated to the community of NORLab. One of the important projects is the authentication authorization, which permits that we can extend the identity service nodes in different locations, in particular in Tucson. So we are ready to start the modifications to authenticate VPN or Wi-Fi or any other using a centralized authentication system, which is very important. For that reason, we are working in order to have the enough licensing, and many new policy statements have been created during this time. The cloud service desk was moved, or the service desk was moved to the cloud in order to have a common tools to coordinate the different initiatives to IT Ops from the clients, from the users of NORLab. Finally, one of the projects that is still in progress is the Google Workspace that has been deployed in all the NORLab institutions. This affects, especially, obviously, not only Gemini, but it's some of the Gemini initiatives that made in the past were very helpful in order to advance with the integration. And another important improvement is to integrate Gemini and MCO as one community, but still we are thinking how we want to do in order to maintain the security, the segments, the functionality, but we are not to open every subnet or VLANs and between the system. For the reason, and during 2020, we create two strategies in order to integrate Gemini and MCO. The first one is in layer 2, just to share some strategic VLANs between the both programs, especially to authentication and Wi-Fi, etc. We are using another strategy in layer 3, just creating a few statements of configuration of static routes. Very simple. We extend the SSIDs from Gemini to MCO buildings. This is another important thing that we did during the COVID. And also we extend the SSID from MCO to Gemini buildings. So we are sharing a common space and we are going in that direction. The voice over IP.
Mauricio, 1 more minute.
Sure.
Thanks.
Eduardo, my case. Yeah, okay. I will finish with mention that we are preparing the Gemini MCO integration with new configurations between the two sites. And we are also creating future activities, especially the Node Lab networking upgrade project. We are doing a LAN design. We will work on the POP upgrade to the next year, firewall upgrade, even to the MCO. And we are creating collaboration and integration with Vera Rubin during the next years. Okay, so to final comments, we are in advance specific to the network update project. We want to have many options on the table, the traditional multi-tier, fabric to create the new technology or architecture to the data centers that will require studying many vendors. And also we are expecting to cover this in at least 3 years. This will involve important Node Lab stakeholders. Okay, here's some example of how to draft the network using multi-tier designs. It's very similar, but it's now we are thinking to open source technologies, not specific for some manufacturer. And the same thing with if we want to use in a fabric, we want to have more ideas on the table. So we are still studying and understanding this. And I think I would like to comment that the Vera Rubin team, or through the Vera Rubin team, we could advance talking and sharing this technology and this knowledge from the data centers and the network architecture. Okay, that is the final presentations. Do you have any questions?
Yes, I have a question. Julio Constanzo from Rubin. I have actually 2 questions. One is regarding the Telconor backup link, the bandwidth, and if you have used that before for science or just for connection between sites. My second question is regarding the Rubin integrations, and it's more about the experience that you have already with integration from CTIO and the MSO into Gemini and where it is right now, Neuer Labs. So how you see the future in the Rubin integration? Thank you.
Thank you, Julio. Well, the first one, the backup link Gemini Telconor, it's really used by science during a night. Right now, it's just backup. It could be something like survival because it's a short or a few bandwidth respect of the total bandwidth they're using the DWDM. But when we are working at night, if the DWDM fail, in many occasions, that link was enough to maintain the operation and science during at night. So we don't have too many cases about that, because one of the things that didn't happen during the night is the synchronization of the some storage that it's normally doing in the morning. So we are not expecting that bandwidth collapse the remote observing. In any case, we don't have more than 2-3 events during the year. How we see the integration with NORLAB is as NORLAB and Vera is a very good question. Yeah, absolutely. It's I think one of the main objectives that we keep in mind in terms of how we'll design the new. This is in particular the network library project. Is perfectly one of the key points in order to think together how we will work to the future. Until now, the network library project is still not in progress. We want to do the kickoff of this project during this year, but due to many other collaborative tools and other projects, it's not starting yet. But I think we need to talk internally how we will do this and how we'll facilitate the integrations. So and from my opinion, we also need to learn more in depth what it's doing Vera Rubin internally. That was my first question that I did to Christian this morning, because it's very important to understand what is the point of view of IT technology from Vera Rubin, because in my opinion, not only has a very good team, IT team, it also has probably more new ideas about how to do some specific solutions. So that is interesting, and that is important. I think we need to be more closer and closer in order to obtain that successful integration.
Thank you, Eduardo.
Any other questions for Eduardo and Mauricio? I would like to make a comment that it's impressive to see the development of the networks there for NORLAB and the integration with the projects like Gemini. I think it would be really interesting for the research networks and NORLAB to have a better understanding of the use cases, because this is a lot of advanced networking technology that I'm seeing here, and it would be really, I think, interesting to better understand these use cases and how the sciences, the different instruments will be supported. So maybe that could be a follow-up action that we discuss with NORLAB.
Absolutely, absolutely.
Okay. Let's see. Next up, I believe, is NREO, David and Adele.
Yeah, I'll be presenting. If you can give me a share screen.
I think you're co-host already, David.
Excellent. Can everyone see that in present mode?
Yes.
Excellent. So good morning, good afternoon. I'm David Halstead, Chief Information Officer for NREO, working with Adele on this presentation. Just to give you an overview, of course, ALMA, the Atacama Large Millimeter Submillimeter Array, is situated in Chile, but was funded about 20 years ago from the 3 regions of the world. No one region could afford to do this $1 billion+ instrument at the time. Of course, North American is represented by the National Radio Astronomy Observatory, funded by the National Science Foundation through a cooperative agreement with Associated Universities Incorporated. Then Europe is covered by ESO, European Southern Observatories, and then East Asia is covered by the National Astronomy Observatory of Japan. And of course, the instrument is run by the Joint ALMA Observatory, headquartered in Santiago, Chile. And the regional centers, or the ARCs, are what I would call the storefront for ALMA, but of course the factory is in Chile. So just a summary of the ALMA telescope. It is an interferometer, taking 66 dishes and combining them through a supercomputer called a correlator to provide images on the sky, very high spectral resolution. mostly at longer wavelengths, of course, for radio astronomy. The array can be subarrayed into to do multiple observations at the same time. There are 50 12-meter antennas. 25 were funded by North America, 25 by Europe, and those 25 dishes are slightly different design, but they all work together. And then the 12 7-meter antennas, and for single dish total power antenna of 12-meter. So 66 dishes in all at 16,500 feet or 5,000 meters in the Atacama Desert. It's in a space mission style, which means that every year there's a call for proposals. That proposal deadline is next Wednesday, so you should be well underway to getting your proposals submitted. And these proposals are reviewed by an international team that basically ranks based on science impact only. So it's a very important mechanism by which we have the best science performed on the instrument. And then the principal investigators have access to that observation that's performed by the GAO for 1 year from delivery of the data. Thereafter, it is made public. At the moment, we're looking at a control room extension because it is a real challenge to fly people from Santiago up to Calama, then over, bus them over to the antenna operations site. So the idea of having the observations done in a virtual control room in Santiago is very attractive, especially with pandemic constraints, which we'll come to in a minute. Of course, this time last year, we had the bad news that ALMA was shutting down, and this was a hard shutdown. The 3 power generators were actually pulled offline, and just a very limited amount of power for the atomic clock was left up at the high site. The good news is that that pause has been lifted, and the array has been observing for about the last month, but it is still very challenging. As folks know, Chile, like the rest of the world, is still gripped by the pandemic. And to do full operations, it needs about over 100 staff, about 120 staff. And as people are probably aware, the array is continually being reconfigured. So the dishes are picked up and moved to alternate pads to give the antenna array different specifications for resolution and total sensitivity. So I'm not going to go into too much detail, but these are the 3 major sites: the ALMA array, the operation support facility, and then of course Santiago. The next presentation will go into much more detail. Likewise for this slide, I'll just breeze over it. This is where we in North America get involved, basically working with the joint ALMA observatory in Santiago, and then Florida International University, RayUna, etc., to move the data into the North American Research and Engineering Network backbone, facilitated by Internet 2. The North American ALMA Science Center is hosted in the University of Virginia on grounds in Charlottesville, Virginia, and of course we do rely on that institution for our local area network. So what are the network requirements? We basically have a steady state of about 1 terabyte a day, but it does very much depend on the network configuration and the array configuration. Basically, the further the dishes are away, the larger the data, the longer the wavelengths gives less data. Very short wavelength observations give more data. And a lot of these observations are, of course, defined by the science that the observer wants to do. So we can talk about averages, but during certain times of the year, in ideal observing mode in long baselines, we might get half the data in just a few weeks. So it is definitely spiked data. There is also several considerations about where the data is processed, and I'll come back to that in a minute. So these are the 3 regions, and it's important to note that there is only a single copy of the archive data at each of the regions, and of course the primary archive down in Santiago, Chile. If there is a critical failure at one of the regional centers, we would try to restore as promptly as possible from Chile, but we would point the archive access for our users to one of the alternate sites. Usually in North America, we'd point at Europe because of the available bandwidth laterally east-west over to Europe. So this was the shutdown notice, March 18th last year. This was the right thing to do, of course, because of the operational mode for ALMA, requiring a lot of travel and people doing turnos 10 days on out of a 2-week cycle. North American NRAO instruments, the very large array, the very long baseline array, and the Green Bank Observatory managed to continue observations because of the geographic closeness of staff and the ability to protect folks in a more controlled, localized environment. But ALMA did do a full shutdown. This is the good news. The array came back on pretty much a year later. And what was decided was that the cycle 7, as it's called, each year is a cycle, would just restart and continue. Cycle 8, as I mentioned, is in the proposal submission phase, and then those proposals will be reviewed and ranked and should start in October of 2021. So this is our typical data rates. And of course, as we look at the Vera C. Rubin telescope, the numbers are a lot less scary for ALMA. We did start earlier, but the typical raw and reduced data per year is 200 to 300 terabytes. So it's very manageable, although I would say this raw data, often the PI needs to do more work on it. So we do have computing facilities and storage available for North American users and Chilean users, anyone appropriate for North American Regional Center, available for further data reduction after the initial round. This is the integral. As you can see, cycle 7, we have just moved through 1 petabyte of total storage for ALMA. I believe the total NRAO archive is about 4 petabytes. So it is, you know, it's petascale, but it's not prohibitively scary. So cycle 6 to 7, the good news was that we managed to move to a single stream of data. There was a concern over the water vapor radiometer, and we did duplicate storage mode, so that actually helped reduce the amount of data produced. The minimum number of tenors is 40. We have just reached that for the restart, and several hundred to 300 terabytes a year is about the normal that we're seeing. As I say, that can depend on the proposals received. And we are moving to the majority of data being processed at JAO before sent to the regional centers. Early on, the data was observed and then moved to the regional centers for the raw data analysis, and then moved back down to Chile from the individual regions, and then distributed out to all regions. So you can see it was a very complex data path. Now it's more simplified. Future cycles, we are of course running in full science. Data coming out of the correlator is a few hundred megabits a second, which is of course very manageable. And we are sizing our archive appropriately. There is a push for a unification of the next generation archive system that we use at all the regions. This will be aligned over the next year or so with the NGAS architecture used or planned to be used for the square kilometer array. So that will be a major simplification for that archive architecture. I've already mentioned the data rates vary, but that average data rate of 200 to 300 terabytes a year is what we've been observing. One perturbation that will happen is in the ALMA 2030 vision. And this vision isn't, we wait till 2030 and then we have a vision. This is the plan for getting to 2030. As I say, the heart of an interferometer is the supercomputer called a correlator that brings together every pair of dishes and pulls in that spectral frequency for each point on the observation. This will be specified. We're working, the links below show you the working group output. We're looking for finalizing the partner to design and build this correlator. Again, we are working with the larger community. The square kilometer array, again, has a lot of energy behind this. So we're looking to align with the requirements and specifications. So we have commonalities there. And this new correlator will have a lot more capabilities. And while, we could see a factor of 100 if everyone opened up, the full spectral frequencies with maximum sensitivity, maximum sampling rate, we expect between 4 and no more than 10 times the data rate. So we're working towards that correlator with an expectation of the next 5 to 6 years. So by 2028, this correlator could well be situated way down the mountain at the operations support facility, as opposed to currently where it's at the heart of the antenna array of 5,000 meters. So that would be a major architectural shift and of course require a lot of fiber optic communications to pull that data down off the high plane. So the summary, the ALMA data rate has been in a way self-modulated by the principal investigators proposing observations that they want to do at the resolutions that they require for their science. So we very rarely run the dish at its full capability. The data rates flowing from JAO to the regional centers has been very satisfactory. We've been very happy with the level of performance and availability. We don't have the real-time requirements, frankly. The observations are taken, then the data is moved down to Santiago. And if that data is made available at the regional centers within a few days to a week, the principal investigators don't know it is in that mission mode of request. So we don't have those real-time requirements. Okay, I believe that's the last slide. Do we have any questions?
All right, David, is Adele speaking also, or?
Adele, I believe, delegated. Adele, any comments, questions?
That's all. You said it perfectly.
Okay, and there will be a later comment from Rob Salina about a very, very crazily exciting next generation very large array later in the afternoon. So please stay tuned.
All right, thank you, David. Those are interesting descriptions of all the flows that you have going to different endpoints. Yeah. All right, let's see, who's next here? Jorge Ibsen.
Okay, let me start sharing the screen. I hope everyone can see that.
And Jorge, I think we're right back on time. So this is very good.
Yeah. Well, I think I need to thank David because that introduction saved me a lot of slides for my presentation. And I'm going to focus on the other end of the ALMA observatory. And essentially, I wanted to highlight two topics that I think were relevant for this meeting. First, the Changnan-Tor Plateau connectivity that I think is interesting. And the second thing is the use of the control room extension to Santiago offices in Vitacura. So let me go straight with the first one, the Changnan-Tor Plateau connectivity. As David summarized in the slides, the ALMA optical path is composed by a portion of dark fiber going from the ALMA, the high side of 5,000 meters. And then we have a lambda O2 through Telefonica, and then we connect in Antofagasta to the VALS infrastructure that was developed several years ago. You can see the legends here. So one of the nice things of this architecture is it's very simple to think about how to keep working in a braided it. And I'm not going to talk about that at the moment. I just want to talk about what all the things are in the plateau. And the Changnan-Tor Plateau hosts or will host a number of other astronomical facilities. There had been conversation in the past to optimize the available communication infrastructure, minimize the use of microwave based solutions. And there are two things to address here. I mean, the first one is a last mile problem from the facility into our connection point, which is mostly infrastructural. And the second is, I mean, how to handle the communication operation in such a way that there is parallel operation without interference between other observatories and operations in ALMA. This is something we started several years ago. Giorgio was part of that team that was looking into this, and I am happy to say that most of the things we discussed are now being realized. Let me see if I can change. Here it is. So one of the things we have is that we have some extra capacity or infrastructure that is not currently being used, and that has allowed to set up two things. First, to set up in the near future a point of presence for Reuna that is going to be present in the AOS technical building in the high side. And through this channel, we can actually get to the point of presence of Reuna and Antofagasta, and from that point onwards, these point of presence will serve all the facilities present in the plateau. The status of these point of presence is at the moment we're revising the memorandum of agreement between ALMA and Reuna, and in my mind it is very close to completion, and I hope to see it complete and sign off in the following, I mean during this year for sure. And once you have established this point of presence, we have the second part, which is the last mile of these other projects. And we have three distinguished regions. We have the region that is nearby Cerro Toco, another one nearby Cerro Changnan-Tor, and another one in Pampa La Bola. These three zones are hosting other projects. And what we have done is, because we had some excess infrastructure, we can establish a connection point for the three regions with a pair of fibers. Each one of these is going to become an MOU. One of them is already realized, the one with the Parque Astronómico Shannon to Parque Astronómico Atacama to serve, among others, the Simons Observatory. And we're working towards, I mean, finalizing memorandums of agreements for the other regions, in particular with Siquet and Tau. And I think this is a good culmination on this idea of rationalizing the infrastructure in such a way that is serving many but at the same time without interfering. So the different status of these other memorandums of agreements are, some of them are complete, some of them are about to be complete, and these two things are going to happen more or less simultaneously. So I think this is great news because it allows to serve a whole ecosystem in this way. And it is, as I said before, the combination of many years of strategizing how to make synergies between the different actors in the region. Once you get into the valves infrastructure for ALMA or the radar point of presence, you are going to get connected to international connectivity, as, for example, David shown in the case of ALMA. So I think this is the most complex but the most interesting exercise in getting a common solution for a number of stakeholders at a very reasonable time frame. Now, of course, I mean, there is also EVALSO is coming to an end, so there are some extensions here, and there is still future work in terms of upgrading the infrastructure between Santiago and well, between ALMA and Santiago. This is still work in progress, so I cannot discuss too many details, but the idea is going to be to upgrade this in capacity or infrastructure to serve better the needs of the future developments that ALMA is going to have within the 2030 project. Well, before I move on, I just want to recognize this is the work of many people, and in particular, it has been a good approach in having these forums to discuss these problems, so we can have synergies with institutions like ESO, AUI, and some others. So I think it's a great approach to these kind of problems. The second thing that David mentioned, that we are now using a control room extension to Santiago office. And I think this is relevant because it uses the same infrastructure we have. And remember, the AOS is connected to our operations site facility. And remote operation is something we are doing already since the beginning. I mean, the operations facility is at 3,000 meters, 40 kilometers away from where the antennas are located. And something we started in 2019 was, well, use the same communication infrastructure to increase the operational flexibility by allowing opportunistic testing activities from Santiago. As David mentioned, one thing is the logistic of putting someone on site. It is there. There are some expenses there, but more importantly, we wanted to have more flexibility, because sometimes some test windows are very limited, and it didn't make much sense to have a person translated to the site to be waiting for a couple of hours of testing. And if something can be done along the lines of when the window is available because of different weather conditions, that person can be just summoned into a control room so they can perform testing and then move on without having to organize a trip to the site. That would have been a good gain. So with that motivation in mind, and inspired by several mining companies in recent years doing pretty much the same on exploring remote operations with similar requirements and constraints to Santiago offices, the problem is similar to some extent and different in some others, but inspired by that example, we came up with a project that is called the Santiago Remote Control Room Lab, that was initiated in July 2019 to develop and implement a virtual extension to Santiago office for operation testing from Vitacura campus. And this is very interesting. This was a project that took about 7 to 8 months to complete. And we did it just before the pandemic reached Chile in full, and pretty much a few weeks before we had to shut down ALMA. So it was one of these things that when you think about it, we were building this facility thinking in one use case. We ended up having the facility just in time to mitigate some other risk, and there were some other interest in having this facility used. So this is mostly work done by Christian, who was the project manager, but encompassed the three areas I have in the department, because once the infrastructure was put in place, we needed to redeploy some software components from our software architecture, to be able to control from Santiago. So what is today basic science operations? Yeah, it took us a while to be able to resume operations, mostly because the complexity of restarting an observatory was not designed to be shut down to the level we had to shut down. I'm happy to report that the numbers of antennas available to observe has been steadily increasing. And of course, we had to put a number of additional risk mitigations in place to cope with the new COVID risks. This is a snapshot that was taken at the beginning of March. You can see here the evolution of the antennas being available. And this has been a tremendous orchestration and effort from many people throughout the organization to get to this point. And the good news is that by March, we had some goals. I mean, we wanted to have a goal of having 32 antennas by around March 10. And we had another goal to have 41 antennas by March 30th. And we managed to get there a little bit ahead of time. This yellow line is the number of antennas that have been handed over and returned from science. But these other bars are essentially how many antennas have been used by science for science, by science operations for science, and what's the maximum numbers of antennas we have been able to use and again at any point during the night. And as you can see here, once we were able to reach these 32 layer, we started to do our first PI observations, and the results in the first month were very encouraging. I mean, I think this is a great news, and we have been very happy that in the last weeks we have been able to use the antenna numbers over the 41 limit. And I want to recognize the big effort that what has been done by everyone to get to this state. Unfortunately, of course, we're still in the, I don't know if I call it second wave or third wave of the pandemics in Chile. So we're at the moment monitoring the situation. We have reached what we call the basic science operations mode. And in the following weeks, we're going to decide whether we're going to stay here, maybe have a step back, or maybe go a step further to baseline science operation, depending how the pandemics continues to evolve. There seems to be a race between pandemics number going up and vaccination campaign trying to decrease those numbers. So it's very difficult to predict what is going to happen. So we're all in kind of a crisis management mode. But having said that, I have to mention that we did it. I mean, exactly, I think it was exactly a year after we were able to do our first PI observation. That PI observation happened to be the last one we did before we shut it down. You can see here a very nice picture of the control room in our office in Vitacura that resembles in the control room at the OSF. You see here that we have a permanent video connection to the site. This is the control room in the at the OSF, and we have two happy colleagues. I mean, being witness of this first observation. This happened mid-March. And in this other one, you can see that redeploying all the software, because we have a very distributed architecture, was essentially painless. We only needed to take into account the new parameters of the network because of latency and some adjustments in the fine tuning of the software deployment. But other than that, this is working. And nowadays, the Santiago Control Room Lab is being used to minimize staff on site. So we have segregated staff in staff that actually needs to be there because there is no other way to perform the work, and some other staff is deployed in Santiago to do observations. And we have a number of new protocols to allow to do safe operations since from the first day we wanted to resume observations. So that's all what I want to say. Thank you very much. I will be happy to take a few questions if there is time.
Jorge, thank you very much. Any questions for Jorge?
Jorge, I know one of the challenges is the reconfiguration. ALMA, breathes, comes out, goes in on the position of the antenna. Are you, running out of observations in the current configuration? How will that constrain operations?
Yeah, actually, that is one of the important things to take into account. There are two factors that we had to take into account when we were resuming operations. First, we needed to ramp up the number of array elements. So we needed to redefine the minimum number of antennas being used for a given observation. And second, that we needed to have enough observations to be able to do some science work. In reality, yes, the number of projects we can observe is finite. We were about to, if we would be able to transition, if we would have been able to transition to baseline operations in April 9th, the first thing we were going to do was to do a reconfiguration. Unfortunately, pandemics told us otherwise. So at the moment, there are two things being carried out. On science operations, they're looking into the remaining configurations and re-optimize what is the arrangement we need to do to continue observing. The senior management is looking into the pandemics, as I mentioned before. And in engineering and computing, we're looking into what is the number of people we need on site to be able to do those reconfigurations and keep running. The numbers, it is 120, and depending on how long it will take us to be in a situation where we can ramp up to baseline science operations, some decisions on data delivery from cycle 7 as envisioned will have to be made. Unfortunately, it's a very dynamic situation, very difficult to predict what's going to happen from one month to the other. So what we decided to do is to make those decisions on a weekly basis because we need to see how things are evolving. If you had asked me this question 2 months, a month from now, when we were just starting, we were planning to have baseline operations April 9. Reality told us that that could not be achieved.
One more question, sorry to dominate. So the imaging the black hole, ALMA was involved in that back, April 2019. We all remember where we were. That was just such an amazing contribution. I know that I believe that in that situation, because of the volume of data and the number of different telescopes involved, that hard disks were used. Has that been revisited for the Event Horizon Telescope and doing real-time ALMA data transmissions in that mode?
Yeah, well, the short answer is not at the moment. We're dealing. We are coming with way too many things at the moment. And actually, something I have to mention is that we're going to perform some VLBI observations. If I remember correctly, it's starting tomorrow, the day after. At the moment, yeah, so you mentioned this is being done through recorders and then hard disks are being shipped. As we get out of this phase where we don't know what's going to happen and we move forward, yeah, I mean, keeping upgrading the network to be able to think about real-time BLBI it is part of the things we need to think about.
Okay, thank you, and thank you for all your work getting the array back online.
Okay, thank you.
That is an excellent point that David brought up as far as the movement of data. And as David knows, and I don't know if you know, Jorge, but we've been having some discussions with the Event Horizon team group since last year. And there has been some progress made with some of the antennas in Europe to start using the research networks. And if, you know, there's one thing that for all of the representatives here for the science projects to take away from our SAACC meeting is the value that the research and education networks can provide you. So I hear you, Jorge, about the complexities with ALMA and the other telescopes involved with the EHT, but I think it's important that we maintain a conversation about how we can work together to bridge that gap. So we don't have disks having to be transported down the mountain, you know, to achieve what can be done more effectively with the research and education networks. And more and more technologies are becoming available to help bridge that gap. So I'll make a note of that to follow up with all of you on that.
Okay.
Thank you very much, Jorge.
I think you're absolutely right. Remember that the original model from ALMA was to transport hard disks, and we never did it. So this is just a different order of magnitude, but the goal is the same. I think chipping this is not what anyone in this forum would like to have.
Good. I'm glad we agree on that. That's great. Okay, let's see. If there's no further questions, let's move on then. I think next up is Mike Nolta for SEACCC.
Yeah, let me see. Okay, can you see my screen?
Yes.
Great. Oops. Okay, so yeah, so I'm Mike Nolta. I'm the software lead for FEAST, which used to be called SEACCC Prime. This is now stands for the Fred Young 7mm telescope. Fred Young was one of our major donors from Cornell. And just a brief list of who we are, because this impacts the network design. So we're a dedicated telescope that's run by the instrument teams, primarily led out of Cornell University, and then the German consortium, mainly at the University of Cologne, and Canada. And that's where I'm located. I'm in Toronto, but this is also led out of the University of Waterloo. And then, of course, our Chilean partners. So we're building a very nice 7mm telescope on Cerro Chajnantor, right next to ALMA. It's going to be 6-meter dishes. We're going to have a primary and secondary. And they're going to be extremely smooth. We have a very large camera, so we need a very large field of view, and very precise pointing. We expected first light currently is late 2023. And of course, the primary number that this group probably cares about is our daily data rate. Right now, it's estimated to be about 3 to 8 terabytes per day. So this is a rendering in situ, and it's mostly just pretty pictures. And then you can see our containers for workspace at the base. And here's just a close-up of the telescope. It swivels around this support cone at the bottom. So this is the azimuth axis. Can people see my mouse?
Yeah.
Yes. Okay. So yeah, so it swivels around the azimuth axis here, and then this box here is the elevation structure, and that rotates around this axis. And then the instruments are located over on this side of the telescope here. Okay, so we have two first light instruments. The first one's called CHI. This is being developed by the University of Cologne. It's going to be a multipixel heterodyne receiver, 2 frequency bands, one around 400 to 500 gigahertz, and the other one up around 800 gigahertz. And this one's going after trying to understand molecular clouds, process of star formation, the dynamics of the interstellar medium, basically by resolving the velocity structure of these gas clouds and doing line mapping. And then the second first light instrument is PrimeCam, and this is rendering here. It's got 7 optics tubes. Each one of them is going to have a field of view of about a little over a degree. This is the outer cryostat. It's cooled down to, the detectors themselves are cooled down to about 100 millikelvin. And so each tube here is going to have a different frequency, but ranging between about 220 gigahertz to 850 gigahertz. And then there'll also be two spectrometers, 2 Fabry-Perot spectrometers. And so this one's now going after cosmological parameters, trying to refine those numbers via either looking at the epoch of reionization, so this is when the first star is turned on, or by mapping SZ clusters and seeing how the SZ clusters, so these are very large clusters of galaxies, and seeing how they distort the cosmic microwave, in this case used as basically a background light. Okay, and this is now just a cross section through the telescope. And this is the support cone down here. So this is the azimuth axis. And then you can see, it's a little hard to see, but you can see the 2 mirrors here. So this is the first primary mirror down at the bottom of the elevation housing, and then the secondary mirror over here. So light comes in the top, bounces off this one, and then into PrimeCam, which is this tube here. I didn't mention PrimeCam is nearly 2 meters. So this is nearly 2 meters tall here. And then CHI will be located down here. And when it's in use, there'll be some swing out optics in here to divert the beam down to CHI. And then some electronic space for electronics racks for computers here. And then the cryo compressors down over in this space. Okay, so we're trying to push, nearly out to terahertz frequencies. So we need to be at an extremely good site, extremely high altitude, because we need to see as little water in the atmosphere as possible. So we are going to be on SAACC Tor, almost at the peak, not quite at the summit. This is near Alma. However, we're now in a new legal regime. As of 2013, anything above 5,500 meters is extreme altitude, considered extreme altitude in Chilean law. And so there are increased scrutiny and requirements and tests, extra medical tests every year. SAACC has to approve every company, and they get reports on every individual worker. And so as such, we can't get direct fuel deliveries to the site. So originally the plan was to have diesel generators at the site, but that is not feasible. So we're going to have to site our generators at a lower altitude and not at the site, and trench power lines up the road. So this is now a diagram of kind of the local layout. So we are located here. So this is SAACC Tor on the left-hand side. At the summit is Tau. And this red line here is the road that goes down the mountain. And we're in the Astronomy Park, and Alma's property line starts here. So that's this dotted line here. So the plan is ALMA has very graciously, well, I don't think we have a formal agreement yet, but I think that's nearly done. But the plan is to put the SEACCC and TAU generators here, a service area near the ALMA road, and then trench the power lines up the mountain. Now, of course, if we're going to be trenching power lines, of course, we have to lay in fiber as well. That's basically free at that point. And so the plan is this service area is near one of ALMA's pads. So this one's pad 409. And the plan is then to also lay in some fiber to the pad. And then ALMA has very kindly agreed to lend us a pair of their dark fibers. So we'll connect to pad 409, and then from using those dark fibers, we'll connect to the upcoming Reuna POP that's going to be at ALMA's AOS. And so we're still working on the formal agreements for both of these connections, but I believe they're nearly done. And so, yeah, and then hopefully once we're connected, I mean, the original plan was to ship disks, but if we do manage to connect to the fiber network, then we'll have sort of two modes of observing. One when CHI is on, and one is when PCAM is on. They will most likely not be observing at the same time. So when CHI is on and observing, then we're going to be shipping the data primarily to Cologne directly, and then a small stream to Toronto for just metadata and housekeeping and that sort of stuff. But the bulk of the instrument data will go directly to Cologne. And so, yeah, so estimated mean data rate of about 700 megabits per second, averaged over 24 hours. And then when PCAM is on, we'll be shipping the data to Cornell instead. And here, a bit less data. So this is going to be about 400 megabits a second. And again, averaged over a 24-hour period. Okay, so that's pretty much the bulk of my presentation. I just wanted to leave you with, we have been sort of on paper for quite a while, but physical progress is actually starting. So the summit has just recently been leveled. We had some delays with the pandemic, naturally, but those seem to have mostly cleared. Manufacturing has begun in Germany, with the contractor Vertex Antenna Technik. So these are some images of the middle section of right above, that sits right on the azimuth bearing. And yeah, and that'll do it. And thanks very much.
Thank you, Mike. Any questions for Mike? So I have one for you, Mike. The fiber that you were describing, is this the same fiber that Jorge was describing?
Yes, exactly. So the plan is to connect to the point of presence at Reuna's point of presence that Jorge described in his talk at ALMA.
Okay, great. Do you have a sense of a timeline for that yet?
Well, like I said, we first light is expected late 2023. So we'll start, so obviously we'll ramp up. So basically, really 2024.
Okay.
For a significant data movement.
Great. All right, well, if there's no other questions or comments, we are, let's see, ahead of time for our break. So what I would like to do at this time, if before we break, let's see, that's the person exactly who I want to see on my screen. It's Jeff Cantor, my co-chair. Jeff, any comments? Any observations before we break?
I think as always, this has been a really good overview of the different observatories and their operations, and I'm looking forward to hearing the rest of them.
Well, good. So before we break, we'd like to take a moment to express our thanks to you for being a chair of the SAACC. And we would like to present you with a gift to show our thanks for this. So I'd like Vasilka to show it to you, since normally we would give it to you if we were able to meet in person, but since we have to do this virtually, we will just
You're in Miami.
you'll have to see it. It's here in Miami.
Okay.
Could
So
everyone, please, if you can, turn on your cameras. I'm going to take a picture, a screenshot.
So
Thank you.
I don't see Vasi with
Well,
with the plaque.
It's been an honor and a privilege to serve as the chair. I hope to remain aware, if not involved, at some level. And I think I'll be leaving the chairmanship in good hands with Bob. And many thanks to FIU for all the years of coordinating and organizing and doing all the legwork.
Well, we're very, very happy with everything, your contributions and your leadership as well. And we want to express our thanks. And we hope that you will stay in contact with us. You're an invaluable resource to our project, and you've been an excellent co-chair, friend, and mentor these years as we've made progress with our project. So there's Vasilka showing you the plaque, Jeff, and we will ship it to you as soon as possible.
Thanks so much.
And so, did we take a photograph?
Yes, I took both screens.
All right, great. All right, well, and we welcome Bob Blum as the new co-chair for the SAACC, and Bob brings a lot of experience to our committee, and we're really looking forward to his leadership and to help us move forward for the new project. So there's Bob. Bob, you want to say anything?
No, just thanks for the kind words. I'll add my thanks to Jeff, and I'm glad he's not going away anywhere fast because we'll certainly want to keep him in the loop of what's going on. It's just an exciting time in Chile for sure, for everybody.
Great to hear that. Okay, so with that, I guess we'll take a break, and we'll break early, and we can come back at see, we're scheduled to start again at 1:55 with GMTO Sam Chen. So we will. All right, so we will see you back at 1:55.
Okay, thank you.
Thanks. Thank you.
Katie? Mauricio Rojas here. Hi. You're muted.
Okay, hi.
Hi. Will be the same link, right? So I can leave the window open and everything will be okay.
Yes, that's exactly right. You can leave the window open. I would put the mic on mute and maybe close the video. Well, you did that already.
Sure.
For other people. But yeah, perfect. We'll see you in a little while.
Thank you. Bye.
Bye.
Hello, everyone. Welcome back.
Thank you. Good to be back.
Let's see. Is Sam Chant? Sam? I see Sam.
Yeah, you see me.
Sam, you ready?
Yeah, I'm ready as I ever be. I need to share my screen, right? So let me see.
Let's see. Do you have? Are you
Look like I
co-host?
do.
Yes, we've given you co-host. So whenever you're ready, Sam.
Well, how about I just shout? Do you guys see the PowerPoint?
I do.
You do.
I do as well. Hi. It's looking good.
Okay, should I run? There are 32 people now, but I think it's my time.
Yes, you can get started whenever, as soon as you can.
Yeah, so I brought my own introduction slide. Wasn't sure how we were introducing in the morning. I am the IT Director and Information Security Officer for Giant Magellan Telescopes. I brought a little, didn't want to move. Okay, so I brought in my little career path. It's a quick snaps. We can move on from there. Just want to say that we are part of the US ELT program. That being said, the US ELT program, there's actually two, right? There is us and the 30-meter telescopes. So I have this slide right here that shows the all these type of mirror telescopes. We are down here at the Giant Magellan telescopes. We will be at Las Campanas Observatory. The other one, the 30-meter telescope, is in Hawaii, and of course the bigger, larger one, the extremely large telescope is the European telescopes. I think these are the three big telescopes that are coming online. Sooner than later. Ours is it's a weight off. Ours has been delayed a little. These are a comparison the size of a telescope to a tennis court and a basketball court down here. I have a little about 6-minute videos that was narrated by our chairman of the board, Dr. Wendy Friedman, and for you guys at Noir Lab, Dr. Patrick McCarthy was the other person that narrated the videos. I think that gives it more detail of what I can ever imagine what a telescope is supposed to do and how our mirrors is constructed. In terms of our infrastructure, I'll go to that toward the end because our infrastructure is fairly simple at the moment, as we are about 7 years from being online. So we didn't have a large infrastructure need right now. So let's take a look at the videos. Let me see if it plays. You guys hear the audio okay?
Yeah, it
I hear it.
coming through.
The surface of this mirror is so smooth that if we took this 27-foot mirror and then spread it out from coast to coast in the United States, east to west coast, the height of the tallest mountain on that mirror would be about ½ an inch. That's how smooth this mirror is.
The challenge with GMT is 6 of the 7 mirrors are portions of a parabola, but they're off the central axis. And in fact, the central axis is not only off center in the mirror, it's way outside the mirror itself. So you have to work off axis asymmetrically and yet put in this beautiful surface. We have to make this optic precise enough so that when the light travels 5, 10 billion light years, it comes and hits our telescope, that we don't scramble and lose that information that's traveled so long. We have to make these large optics to a 20th of a wavelength of light, even though it's 25 meters across. It's a challenge of about 1 part in 10 billion in terms of precision manufacturing. So it's an extraordinarily challenging process. right now, we are in the process of developing 4 of the 7 mirrors that go into the telescope. That is, the first mirror is completed. The second mirror, we're grinding away on it. The third mirror, we're building up the mold and we'll start melting the glass in August. And the fourth mirror, the glass and the mold materials are already coming in and being sorted in the warehouse in Tucson.
Each of these mirrors, the glass alone is 20 tons of glass in each mirror. There are 7 of the mirrors. There's a mount made of steel that has to hold the mirrors, the structure, the instruments, the top end of the telescope where there are secondary mirrors. We have to measure the distance between the primary mirror and the secondary mirror to 1 part in 500 million. And then focus light to a fraction of a wavelength of light. It's an astounding, astonishing challenge. And this enclosure will be the height of a 22-story building. It's not an ordinary building. It has to rotate so that you can point the telescope in the sky and look out and see distant objects.
It has cranes, it lifts things, it has air conditioning, it has heating, it has power, it has liquid nitrogen, liquid helium. This is a complicated business, and it's a dance between the telescope and the dome. They all have to play together and work together to make sure the telescope delivers what it was built for.
So all of this elaborate structure that we have to build is really just to receive a small number of photons of light that are coming to us from distant space, hit this small little patch where we set up these mirrors and allow us to address these mysteries that we don't yet understand about our universe. It's like Ferdinand Magellan, after whom Giant Magellan Telescope is named. Here he was coming around Cape Horn. There was a whole other ocean there to be discovered. We don't know what's out there, but we're setting sail to try and discover what's out
there. We've learned in recent years, in the past couple of decades, that massive black holes are common, but in fact, almost every galaxy has a giant black hole at its center. And extraordinarily enough, there seems to be a roughly constant fraction of the galaxy's mass in the black hole. So we don't know, did the black hole come first and the galaxy grow around it? Did the galaxy build and the black hole formed after that? Where did all the stuff that went into the black hole come from? Did they grow by merging with other black holes, or did they simply feed, or they go through a gluttonous phase where they swallow stars whole to become so massive? Right now, we can only see in any detail a few of those black holes, the ones that are either the nearest or the most massive. GMT, using the power of adaptive optics, will allow us to look at giant black holes almost anywhere in the cosmos, and will allow us to look at the small ones, the seed black holes, very nearby. As we try to track down the mystery objects, the strange beasts, the gamma ray bursters, the neutron stars, things that we haven't discovered yet that will go bump in the night because we don't have good time coverage, that's where we'll stumble upon these new discoveries. Neutron stars were discovered almost by accident. A whole host of phenomena were discovered when we could first look into the infrared. So I expect that as we sleuth along trying to solve the mysteries that we can see, we'll bump into new things.
We are only beginning to scratch the surface, the tip of the iceberg, and learning about planets. How do planets form? Are there other planets in addition to Earth that could have life on them? Right now, we have faint images come from the Hubble Space Telescope, taking the deepest pictures of the sky that have ever been taken. And we only see faint little smudges. Giant Magellan Telescope will have 10 times the resolution of the Hubble Space Telescope and the ability to take spectra of these most distant objects. We will witness directly the first galaxies forming, the first supernova forming, the first black holes forming, and see how the universe that we're living in now, that we see so directly, came to be. We're now embarking on a new adventure. We're building a telescope that's larger than any in existence. We don't know what discoveries await us, but that's part of the excitement and the challenge of building this new project, this new telescope.
Okay, so that is what the GMT is supposed to do. There are all the mirrors is 8.4 mirrors, which is about 2-story height if you stand them on the edges. All of our mirrors is being cast at the mirror labs. It takes about 4 years from beginning to end. So we've completed mirror 1, mirror 2. 3, 4, and 5. So in various stages. Mirror 6 was casted this year. So in 4 years from now, Mirror 6 should be done. And I guess next year they will, if funding permits, they will cast Mirror 7. So that's the status of our mirrors. Let's see, in terms of constructions, obviously we were impacted by the coronavirus like everybody else. This picture was taken February 21st, 2020. That's a summit at Las Campanas. That is the base, the platform where where they will hold the mirror. So that has been completed, all trenched out. The utility tunnels are all built, but that's it. It's been on hold for about a year now. The other project that is important also is the water package. Obviously, can't do a whole lot without power, water, and internet. So the water package is mostly done. About 95% of it is done. It's also impacted by the COVID. Currently, they're working on the programming, with the PLC, testing to make sure, the tank holds, there's no leak along the pipe. So water pressure testing, things like that, fire hydrant testing. So we're there in the testing phases. Once the water package is done testing and, put into use, I think we should be on a little hiatus until we get some more funding from NSF. That's what they're heading for. So they're doing all the paperwork and what is required, hopefully, to get some more money to build the telescope. In terms of scientific data, we are projected to get about 10 to 40 terabyte per night. Obviously, there are no data. Our first light scheduled to 2028 right now. Originally, when I started in, what did I start? 2017. It was supposed to be 2023. Now it's 2028. So I don't have a lot of infrastructure in place at the moment. What I'm hoping to do, I come to these meetings. I'm hoping, as part of the NSF, the scientific data will ride on the research or education networks. If I am lucky, if we have the fundings, there are 8 strands of fiber that goes from La Serena to where we are now. It's owned by a company called Movie Star. So we have 2 internet circuits going through there. I think 3 now that's going through Las Campanas Observatory. And then there are some spare fiber that's running through there. But ultimately, if we have the funding and we are doing new power line that goes from the summit all the way down to the street, like Mike was saying, while you're trenching the power line, might as well throw in some fiber along that line. So if we can throw the fiber all the way to the street, maybe we can lift that fiber and send it to La Serena and hook into some database or actually some data center where we'll use those as just dark fiber from our summit to the data center. Also because I haven't been told where the data will go yet, right? We haven't gone that far where, where we need to move the data, where, we will have a copy at the summit, obviously, but the rest of it, I haven't been told where we go, right? We have a lot of partners, we have Australian, Japanese, South Korea, we have Harvard, University of Texas, University of Arizona, and a few others, but I don't know whether, the data resides in one location, they access it, or we have to deposit it into all of their data centers. So, that will be worked out, I guess, later. And once they tell me what to do with that, we'll figure out the connection. So maybe I have a couple of years yet. In terms of our Infrastructure, it's fairly easy. It's fairly simple. We run everything through the internet right now. We have no dedicated fibers, no dark fibers. We just subscribe to the internet and we go. So our corporate office is in Pasadena right now. We'll be in Pasadena probably until first light, in which case we will transition the data center to the summit at Las Campanas. We have an office in La Serena, but we kind of, that's a small office. So I think that during the pandemic, we took that office down. We also have an office in Santiago. I have been pushing a lot of resources into AWS because, as offices move around, things like that, I don't know, if it's wise to just have a data center at the moment, especially for operation, right? I mean, our office can change. If we're at AWS, we could just connect to it directly. Now, all of our site right now has a redundant internet connection, but it's just basically, an internet connection that we purchased from separate companies. Okay, let's see. In terms of our data structures, there are not a lot of data. We grow by, we'll probably do 5 to 7 terabyte a year in terms of operational data. So we back that up locally every hour, and then on a nightly basis, we push to our cloud backup. We also replicate a whole data center. We replicate it to the summit. So our summit becomes our disaster recovery site right now. It may be in reverse if, once we come online, we may do a co-location somewhere where we replicate the summit to some other location. But our AWS data, we back that up nightly, and like I said, we are moving as much resources as we can to AWS, except for all of our SQL servers and things like that still reside locally, because those snapshot takes a while to run. I think that's actually all I have for GMT right now, because like I said, our infrastructure is fairly simple. We are not complicated. Maybe in a few years we will be, but right now it's just operational database. We do use leverage a lot of AWS and a lot of Microsoft stuff, to work with our partners and things like that. So we use a lot of web bases for that. The internal stuff is just the regular file sharings and our SQL database and things like that we built. I think that's it. If there are any other questions, you can.
Sam,
yes.
This is Jeff. I do have a question. Could you go back to your slide where you were showing the data rate, and you said you weren't sure where the data was going to?
Yeah, so hold on, let me see if, did I stop sharing or is it still there?
Yeah, I think you stopped.
Oh, I was sharing the PowerPoint presentation, right? So hold on. Sharing. Let me get the PowerPoint back on screen, sorry. Okay, there we go. Let me screen share the presentation, right? This guy. Okay, do you still see it on? No.
I don't see it yet.
I'll do it screen 3. Here we go. Oh, I have to click that and I click share. There you go. Do you see it now?
Yeah. So I'm looking at the first line there of 10 to 40 terabytes per night. That seems considerably higher than the numbers I had heard before. And certainly you're not going to do that over Internet 2 or Internet 2.
Correct.
Could you elaborate on that one a little bit?
So this is, so I got these numbers from our operation team. They were all expecting it, that much data, because I was looking at it and I had to do a calculation. I'm like, okay, 10 to 40 terabytes. That means I need, 3 to 10 gigabit bandwidth to transfer it over a 12-hour period down the mountain. Or unless I have a dark fiber from the summit to a data center, like in La Serena, and then we can just transfer what we need, right, to there. And then once we get to La Serena, inside a data center somewhere, and then we can push that data out to where we need to go. But this is from our operation side that they told me. It may be less. I hope it's less, but you know, it all depends on, you know, what they're trying to take that night, I guess.
Well, good to know. I had heard numbers quite a bit smaller through USELT, so we'll certainly follow up with that.
Right. Yeah, it's better to overbuilt than you know, underbuilt, I guess. But that's what they gave me.
Sure.
Sam, question for you. You're planning to use the research networks in Chile to transfer your data to your archive sites. Is that correct?
Well, I'm hoping, you know, as we move forward, we will, you know, I'm thinking that the rest of our stuff will be funded. A lot of it will be funded by NSF. And then being that we're funded by NSF, I'm thinking that NSF would tell us, you know, where they want the data, because they may be the majority stakeholder, right?
Right.
So I'm hoping to do that. If not, you know, like I said, they have not told me where I need to move the data to. Right now, we plan on having a copy at the summits, but obviously we want to have it somewhere else, and I'm sure our partner want to have it as well somewhere. Right? The Smithsonian may tells me to drop it somewhere in their data center, or you know, in Illinois or somewhere, but that, you know, that it hasn't been worked out yet, or it hasn't filtered down to my level.
Here, Mauricio Rojas. You mentioned something about a computer center in La Serena. Are you planning to build a new one?
Nope. Not trying to build a new one. You know, I'm hoping to see if we can leverage or partner with existing data center. Maybe you guys at Noel Lab, or you know, or Rubens, you know, the LST data centers. You know, or you know, subscribe to some, you know, some kind of internet bandwidth somewhere where I need to push the data to. But I think La Serena right now is the closest large bandwidth that we can push out.
Sam, here Eduardo Toro from Noel Lab. I have a question for you. In terms of the data center technologies, to have a combination IT, business, and operation technology, have you been evaluating some kind of a special technology to develop GMT? Thinking that we have an industry, some Ethernet more oriented to real times operation?
So I haven't been told if the operation is real time, or we are taking the data and then bring it down and then store it and then transfer it somewhere, right? I don't think we're doing high resolution real time.
Okay. And in terms of the technology of specific, for example, industrial Ethernet, IP, EtherCAT solutions, or any other kind of that flavors Ethernet, just so if you are evaluating that.
So so the software and control, so all the control to the telescopes and all the data, I believe it's moving through either high-speed fiber internally, or EtherCAT, right? All the controls for EtherCAT.
Okay, thank you.
Thank you.
And then we parse it out. Of course, in the in here, it's separate layers. So you got the internet, you got the corporate networks where people do their works and things like that, and then the software and developmental network where, you know, all software and control built and to do what they need to do. And then once they're finished, they push it into the control network, which is further isolated, right? So how the design work, or how I envision it, is if we have a partner that need to help with the application, things like that, they will connect to the developmental network. And then they would VPN or direct connect to it. We're also looking at zero touch at the moment, but it won't be done for another year or two. Zero touch deployment and zero trust, right? But so like our software guys, like hey, I need some guys in Brazil to upload stuff and then to work on our developmental server. So we would drop them into the developmental server, and then that's it, right? We have a special VPN into those locations so that they would only have access to that one server.
Okay, I think we're ready to move on to the next presenter, which is Simone for the Simons Observatory. Simone, you ready?
Yeah, let me try to share the screen. Just 1 second, I want to try to do a portion of the screen. Okay. And you should be able to see the slide. Is that fine?
Yes.
Okay, great.
Yes. Mm-hmm.
Okay, so yeah, I'm Simone Ayol. I'm here to present a status update from the Simons Observatory. And I'm very much speaking on behalf of the entire Simons Observatory collaboration. And as any good observatory is good just as the people. And so I really want to show you all the collaboration, the students and postdocs and faculties at different institutions in different parts of the world that in this case we met in Berkeley about 3 years ago for one of the face-to-face meetings. And this project, as I mentioned, is part of a large collaboration of institutions around the world and is mostly funded by the Simons Foundation with a contribution from the Heising-Simons Foundation as well. And we're called the Simons Observatory. I was presenting last year as well, so I'll try to give you an update on what has happened in the past year, but also just a quick reminder of what SO does for the people that were not here last year and haven't heard about the Simons Observatory before. We are a SIMBI experiment, so we observe in the millimeter wavelength, and we sort of have two big objectives that are reached with two different types of telescopes. The first one is sort of a high-risk, high-reward science. We are looking for the signature from inflation. And that's usually done with telescopes that don't have a whole lot of angular resolution, but it can control systematics very well. And the idea is that you will be looking into roughly 10% of the sky that is very low dust contaminated, for whatever low dust might mean. And we look for large-scale polarization across the sky, specifically what we call the B modes. And in excess of B modes, large scales might be a smoking gun for inflation. So here you see in lighter color the survey that we expect from what we call the small aperture telescopes. And there are 3 of those I'll show you in a second. And they overlap with existing surveys from Balloon and from the South Pole, the BICEP-CAC. And then we have another set of science goals, which include understanding primordial perturbations, the neutrino mass, looking at the number of relativistic species, the epoch coronization, dark energy, galaxy evolution, and the transient sky. And that really requires 2 main things. You want high resolution, so that's a big mirror, or big for millimeter standards. You want a lot of the sky. You need to cover a large part of the sky, especially for when it comes to measuring properties of neutrinos. And so with the large aperture telescope, we plan to survey roughly 40% of the sky. And the current plan is that the survey will basically overlap with the Rubin Observatory LSST survey plan, and we heard from Bob before, as well as with other large-scale structure survey that are currently existing or they are operating, such as the SEDES and so on. And the idea is that often the science requirements or science goal do require cross correlations between CMB products with large-scale structure surveys. And so the idea is that we will be acquiring a lot of data, and we will periodically release such data to the broader community in the form of CMB maps or lensing maps that have been reconstructed from these multi-frequency CMB maps, source and cluster catalogs and those wavelengths, as well as information about transients events that will happen as we survey the sky with the large aperture telescope. And so I'm at this meeting, which really means we are observing from Chile. And here you see a picture of the plateau that I believe I showed last year as well. Here you see Polar Bear and Simon's Array, ACT and CLASS that are operating and have been existing for a long time. And this is where we plan to place SO. In this direction, you have ALMA, and down here you have San Pedro de Atacama. And of course, this is a sweet spot for us in Chile for two main reasons. To do CMB science, you really want to observe in the frequency range between roughly 20 to 300 gigahertz. And so that's what we plan to do. And at this height, the precipitable water vapor is of about 0.8 millimeter on the median one. And so this is really good for these sort of frequencies. Of course, as we heard from Mike, you want to go a lot higher to access higher frequencies in the case of SAACC prime. But the other important part of Chile is that given your minimum elevation you are able to achieve with your telescope, given the surrounding area, you actually have a lot of sky that is observable. And with a common 30-degree lowest elevation, you can see that you can, in principle, observe 80% of the sky or more, although we're targeting 40% of the sky, at least for this survey. So Chile is great, and we've been doing CMB science from the plateau for a very long time. So what's the update? I showed you the site. That's where we plan to put it, and actually excavation has started. And so you see then from the 2020 meeting to the 2021, the site construction is underway. On this side, you see the foundation of the high bay. So here we'll be having two buildings. One is the lab that will contain some computing for the site, as well as the high bay to integrate some of the hardware when we get at the site. Whereas on the right side, you see the first foundation of one of these small aperture telescope, the platform. So the platform will sit on top of this. And here around you see the excavation for the ground shield, which actually the pouring has happened. And so as of right now, we do have both foundations ready to go, waiting for the SAACC to be installed and the ground shield that covers the small aperture telescope. And so the site is going great. Of course, COVID is a challenge for everyone, but things are moving forward. And we do expect connectivity to the site before the end of 2021, which really means having full power, or at least power for our computers, buildings to host these computers, and at least a remote connectivity that at the moment will be with a radio link, a line of sight radio link between the site and San Pedro de Atacama. So in this direction, basically on the same model that was used for all the other experiments at the moment. And that will give us enough connectivity to make sure that the site team is always in connection with North America for safety and other purposes. So that's happened. In terms of the instrument, just as a reminder, we plan to have a total of 70,000 dichroic detectors. So each detector can look at two different frequencies. And these detectors are operating at 100 millikelvin inside beautiful fridges that have been constructed. And these detectors operate in a low frequency range between 27 and 40, mid frequency 9150, and what we call ultra high frequency 220 to 70 gigahertz to 80. So here you see the detectors. Such detectors will go roughly half in the large aperture telescope receiver. Is a huge cryostat that reaches these temperatures. And three of the small aperture telescopes. Here you see the receiver as well as the aperture with the lens. And there is a rotating half-wave plate that is used to modulate the signal for systematics. And these cryostats are installed in the large aperture telescope. And you have seen this from Mike. We share the same design with SAACC prime. So also this one is built at Vertex with the same design. SAACC prime has higher specification in terms of surface roughness for the mirror and precisions in pointing. So for us that we do millimeter, we do like lower observational frequencies. Actually, those specs are, we have less requirements. So that's very good for us. And so we share the same design and Vertex is building it. And this is the small aperture telescope platform that I mentioned before. So I showed you this slide last year. Where are we this year? With detectors, we are starting to do testing. So we have detectors and we have the connected readout for those detectors. And now those are in different institutions such as Princeton, Cornell, University of San Diego. And these detectors are being tested right now to make sure that the performances are as desired. In the previous slide, you've seen the receiver being delivered after now is being outfitted with all the different components for readout, cooling, and so on. Here you see from Vertex, this is the azimuth part of the large aperture telescope. So this box will rotate along this axis, and here there was some metrology to show that this movement is working fine. Here you see the small aperture telescope. Again, the one before was just a box that was delivered. Now it's been outfitted with the cryostat and also some of the readout and detector components that need to be tested. And for the SAT, we actually have the first SAT platform has been finished by Vertex and delivered to us. They are now moving to the other two platforms. And here you see us doing factory acceptance testing where we were able to test motion of this platform along the azimuth direction. All the telescopes will pick an elevation and scan in azimuth back and forth throughout day and night. Of course, we pick the elevation, we change the elevation once in a while. And what I want to point out is that all of this was actually possible through the amazing job of the DAC team or data acquisition team that is part of data management, who built from scratch since 2018 a full integrated observatory control system. It's a modular system to be able to talk with all the different telescopes and modules that we have at the site, gather the data and communicate it back to the computers at the site, and then being able to ship to North America. Includes alarms for the site for safety, and of course a user interface that can be accessed from North America for operations. So great job. And actually yesterday we had 1 day of review of all this work, and tomorrow we have 1 more day of this DAC review, and we're just really pinning down the few things that might be left over before we start full commissioning. You may wonder about the timeline. So early 2021, there is a lot of testing and validation, optical validation that happens. Mid-2022, we expect first light from both the SAT and the LAT. Early 2023, we start the first science observation. That's when we expect it, where we have enough detectors and we think we have characterized it good enough that we can start getting data that could be used for science. And then there will be full deployment and start full science observations mid-2024, and that's when the project will be fully delivered. And so the SO construction project is from roughly 2016 to 2024. Operation will start after that, and they consist of a 5-year survey plus 1 or 2 extra years after the end of observations to finalize all the data reduction and deliver products to the community. Of course, we do plan to deliver roughly yearly products, but as you finish your survey, you'll need some extra time to finalize the data that was acquired last. And as a matter of fact, a few months ago, we had the first SO operation review, was an external review where we basically reviewed the overall, the draft of operations, how we envision doing operation over the 5 plus 1 or 2 years, and that went well. And we will continue to finalize such operation until basically 2024. So let me tell you briefly how the data distribution works. Those are our telescopes. We have a network at the site that will communicate with our site computing, and we will have communication from the high elevation facility to the low elevation facility through a radio link, at least to start with. And that will give us access to through remote control, simply connecting through the internet. Data will be stored at the site up to a month in 2 copies, but we envision to move such data through fiber, and so that we expect the data to reach North America within 24 hours. I should say that we don't have requirements like LSST, where the data needs to reach North America in a short amount of time. Some of the analysis will be done at the site, but in general, things like transients that require fast turnaround of data analysis could be done partially at the site or in North America, but again, with the latency that doesn't have to be the 60 seconds that LSST has mentioned, just because the project is completely different. And so the primary data path to the link would be to move the data through to the San Diego Supercomputing Center, where the Simons Foundation was the primary funder as computing resources. And the secondary path would be to move it to NERSC in case the SD center is down. But then once it reaches North America, we'll be distributing this across 3 centers to keep 3 copies of the data before erasing it at the site. And so there has been discussion between NERSC, Princeton, and San Diego now to make sure that this can happen. I know that the motto of this meeting is no disks, and we want to keep that. But at the same time, we also have a plan for what we call sneakernet, so the manual movement of disks. This will be helpful just as a mitigation of risk in case the fiber link is not finalized before we actually deploy. The first platform is scheduled to reach the site very soon, so we really want a way to move data. Some of them can actually be moved through the video link. It's not a high data rate for now, it's just going to be pointing of the telescope, but we also want to have a motion of disks, a manual motion of disks to make this happen. So we have baselined this, and there is a unique software that can handle movement through the sneakernet or the fiber, so as well as moving through the US. So all of this is fully integrated and is part of the plan at the plan right now. So a bit of data rates. As I mentioned, the 70,000 detectors are roughly split between the LAT and the 3 SATs. SATs, just because of a bigger beam, don't require a very high sampling rate. And so that sampling rate ranges between 27 to 200, depending on the frequency and what kind of assumptions you make, is actually mostly determined by the spinning frequency of the half-wave plate in front of the detectors. And for the LAT, of course, that's a frequency-dependent sampling that we have, just because the beam size will also depend on the frequency. And so those range between 30 and 340, again, depending on the frequency, but also on the assumptions you make about the telescope. So right now we are baselining the maximum sampling rate just for safety, and that leads to roughly 132 megabits per second in terms of data rate throughout the day, and we can observe day and night 24/7 basically. So during commissioning here, you see the number of detectors as function of date that get deployed at the site, and then we reach that 70,000 mark, and then we'll have a little bit of time to final testing, and then we start operations. And in terms of data volume, again, we are baselining the red curve here. We will basically reach, after full deployment, around 40 to 50 terabytes of data per month, and that will continue through operation. And that will lead us to roughly 3 petabytes of raw data after the 5-year survey that will exist in North America. And then, of course, we'll need to reduce that data to make those maps and related simulations that come with. A bit of update again on all of this in more detail. We finished the specking of the site network layout, making sure that was reviewed for safety, making sure that we also always have connectivity around the site, especially during commissioning. And here you see that there is redundancy, even for the radio link. And I mentioned about the sneakernet plan. Definitely of interest for this group, how do we move the data to the US? I showed some of the slides last year, so let me tell you the update on that. We wanted to review the site network. As I mentioned, that has been done, and so now we know how things are going to be working at the site. Initially, we baseline to have a fiber that will connect to ALMA, as we heard from Jorge, to the ALMA-Reuna point of presence near the pad 208. That has changed now is the Parque Astronomico that will be providing that fiber connectivity to the plateau, because now there is interested for not just SO, but for multiple experiments. So it won't be SO anymore, but that will be the Parque Astronomico. And so there was an MOU written between SO and ALMA that included a lot of safety, but also this connection. And that MOU has been signed and is basically now kept mostly for risk mitigation in case there is any delay from the Parque Astronomico. But now the baseline is that the Parque Astronomico is working with ALMA for an MOU to make that connection happen. And then SO is building an MOU with Reunion, who will be our provider for this service. So this is roughly the path. Actually, let me go to the next slide for more detail. The idea is that SO will be managing the connection as of right now at the plateau. So there will be a router that is managed by the Summits Observatory, and all the different experiments, including SO, will be connecting to this router. Silica will be installing fibers down to, I believe, what is pad 208 under contract to the Parque Astronomico. We'll be using part of the this connection, this yellow connection, the one that Parque is discussing with ALMA and Silica. Will actually be using fibers that are already owned by Silica for the ALMA path, and then we'll be connecting to the Silica point of presence. And then we'll be running on fibers that ALMA is allocated to the Parque Astronomico for this infrastructure. And those are, again, regulated by an MOU between ALMA and the Parque Astronomico. Once we get there, Reunion will have the point of presence as currently has, and so we'll be able to connect to the current infrastructure, basically using the same fibers, but working on a separate OUT2. So we will never, we don't want to interfere with the network from on ALMA. And so everything will go back on these silica fibers all the way to Calama and then Antofagasta, as Jorge pointed out. And then in the next few months, we'll actually be continuing our discussion with Reunion to make sure that everything is fully operational here. But we'll start discussions to make sure that after the data gets to Antofagasta and then Santiago, we'll make all the way back to Miami to get to the North America, and then we distribute it in San Diego, NERSC, and Princeton. So we'll likely be mediating with Reunion, but there will be discussions with the providers likely to reach North America, many of which are at this call. And so, as I mentioned last year, and I believe was also said before, all of this has been tested, at least partially, and the test was done now more than 3 years ago. James Aguirre was part of it as a SO person, but also Eli Dart, who's at this call, really did great work to really make this happen. And was testing basically connectivity between the ALMA point of presence to NERSC, and basically just connecting a laptop at the point of presence, so it wasn't the full the full hardware that we expect for SO. But basically the performance was better than 700 megabits per second, which exceeds more than a factor of 4 SO needs, which basically also means that we can catch up on data in case there is an interruption of connectivity and we need to sync data that was backed up at the site. That was reliable more for a month. And all these constraints that were found during these tests were basically just because the hardware that was connected, the positive presence, wasn't powerful enough. So we expect actually more from the connectivity after we put the SO software, the SO computing hardware. And again, this was great work between YesNet, Reuna, Red Clara, Amlight, and SO a few years ago. And now we're also discussing this very closely with SIMBS4, and I'm sure Julian in the next talk will tell a lot more about plans for the future after that 2029 for us. And I guess I'll stop here, and I'm happy to take questions if there are any.
Any questions for Simone?
Maybe a comment from me?
Go ahead, Jorge.
Just to provide you an update, the MOU between ALMA and the Parque Astronomico is already signed. And so that portion of the deal is done.
Perfect. That's great news.
Well, that is very good news. A comment from me as well. Sounds like there's been excellent progress since last year, Simone. This is really excellent, and I'm happy to hear that you're already in discussions with Reuna about your network connectivity. That's excellent progress.
We do hope to get the fiber at least a year before full science mode, so 2023. But the sooner the better, of course. So I think we're working towards the direction, and Reuna has been very helpful, as well as Alma and the other members.
That's fantastic. Thank you very much.
Thanks.
Okay, I think CMB S4, Julian, you're up.
Thank you very much. Let me just share screen. So unfortunately, my home network doesn't support both my video and my daughter's schooling, and she takes precedent. So I'm going to thank you very much for the invitation to present here. I'm going to talk about CMBS4, and because this is the first time we've been at one of these meetings, I was going to give more of an introduction. It follows very nicely from Simone's nice talk on Simon's Observatory. And I'm one of the collaboration co-spokespeople, and I'm also the project data scientist for CMBS4. So what is CMBS4? It's the fourth generation, that's the fourth generation ground-based CMB experiment, but it's the first ground-based CMB project in the way that those of us who run agency-funded projects know and love. And that means it's a couple of key distinctions between CMBS4 and other CMB ground-based CMB experiments is that we start with critical science thresholds to define the project, not what's the best we can do under a particular budget cap, and everything is project based, so it's based on can't fail, not best effort. But this also gives us the opportunity to take the full scope of CMB science and make it available to the entire community. We can use the best technologies, the best techniques, the best teams from all of the previous experiments, bring them all together in a single sort of Uber experiment, and then as a consequence, make the full scope available to the whole community, not just the science you can do with one of the precursor experiments. And this is planned as a joint DOE, high energy physics, and NSF, astronomy, physics, and polar programs project. And again, those of you who live in project space will immediately look at the list of 2 agencies and 4 organizations or divisions within those agencies and blanch. But the idea here is that we're going to add the DOE capacities and capabilities, the kinds of things that DOE labs can provide, to the long-standing NSF CMB program, and in this way enable scaling of all the techniques and the technologies to an unprecedented level, basically 10 times larger than any previous experiment. So just some background, the CMB community came together in 2013 for the SNOMAS process and converged on this. In order to do the next generation of experiment, we're really going to all have to come together and propose one single super experiment. We were fortunate in that P5 recommended CMBS4 under all budget scenarios. So that got DOE high energy physics and NSF physics on board. In 2015, we had our first workshop. They've been held twice a year ever since. 2015, also, the National Academies identified CMB as one of the 3 strategic and Antarctic science priorities. So that got Office of Polar Programs on board. And basically, since 2015, we've been kind of waiting on Astro 2020. So in the meanwhile, the SAACC convened a concept definition task force to show what CMBS4 might look like. Then unanimously accepted the report of that team. And one of the recommendations of that team was that the collaboration should form officially. So the bylaws were drafted and voted on and approved, and we became an official collaboration. I was elected one of the 2 initial spokespeople. And then in 2019, based on all of this work, DOE took critical decision 0, identifying the need for CMBS4, and NSF provided some pre-project funding start developing the preliminary design. So as I say, we're waiting on Astro 2020. CMBS4 was one of the projects that was fully traced by Astro 2020. And last year, DOE selected Berkeley Lab as the project lead lab. So somewhat similar to what Simone was describing, we have our primary science goals. These are the things that will define the experiment. So testing models of inflation by measuring the tensor to scalar fluctuation ratio, determining the role of light relic particles in the structure of evolution of the universe, measuring the emergence of galaxy clusters, and exploring the millimeter wave transient sky. The experiment that allows us to do this and to reach the critical science thresholds in each of these 4 areas will inevitably enable a huge wealth of other science, and the CMB and the millimeter wave science that goes along with it when you're looking for the CMB covers the entire history of the universe, from the primary anisotropies probing the Big Bang, the secondary anisotropies probing the formation and growth of structure in the universe, and then the millimeter wave sky as a frequency, as a wavelength survey that can contribute to multi-messenger astronomy, and particularly in this emerging field of transient science for millimeter wave transients. Just to put it in some context, this is the landscape, the US CMB landscape in the 2020s as it looked in 2018, so pre-COVID. So pretty much everything has shifted, or everything that's in sort of construction operations has shifted out. But you can see that we've had this long history of having experiments in operations, experiments in construction, experiments in development, and so there's kind of 3 generations of experiment going on at any time, and then we scale up in size, and in particular going from sort of 10,000 to tens of thousands to hundreds of thousands of detectors on the sky, as we push to greater and greater sensitivity to hit these science goals. So we have our 4 experiment design drivers: the inflation, the light relics, the galaxy clusters, and the transients. And we have sort of 5 design parameters we can tune. How deep are the maps we make? What kind of area do they cover? What angular resolution are they at? How often do we observe the sky? And what frequency coverage do we observe at? And we can tune all of those to the requirements of each of these science goals. And so the inflation goal in particular, this sort of smoking gun of inflation, the B mode polarization that everyone is desperately chasing after, that requires extraordinary depth. These are nanokelvin fluctuations on a 3 Kelvin background. This is tiny signal buried deep in the noise and the systematics, so that requires extraordinarily deep maps. The other science goals require deep maps, but not quite as deep. Turns out that for the inflationary goal, we can actually deal with a fairly small sky footprint, whereas for the light relics, the galaxy clusters and transients, we want a very large area. For the angular resolution, it turns out that for the inflation we can deal with relatively low angular resolution, because the B mode signal we're looking for is on fairly large scales, except that it's contaminated by the lensing of the E mode signal. So we also need a moderate resolution coverage in order to be able to subtract out the lensing modes. And again, for the light relics and for the galaxy clusters and for the transients, you can see how the resolution, obviously for the clusters and the transients, you need very high resolution. The light relics require moderate resolution. The transients are the only piece of the science case that has a cadence requirement, and we're specifying a daily cadence there. And the frequency coverage, you can see that we need very wide frequency cover, as wide as possible for inflation, again, because of the challenge of systematics and removing foreground contamination, and moderate frequency coverage for each of the others. And then in order to achieve those, the map depth depends on how many detectors you have and how long you look for. The sky area depends on where you look from and how you look. The angular resolution depends on the mirror size, but also the mirror quality. I'll come back to that. And then the observing cadence is a survey strategy function, and the frequency coverage depends on your sites and your band passes. So just looking at how we've put that together, the band passes are particularly important for removing galactic, from removing foreground emission, particularly galactic dust and synchrotron. You'll remember the BICEP claim of 2013, I guess it was, 2014, that turned out to be dust because they didn't have sufficient frequency coverage to discriminate between the CMB and dust. It's absolutely critical that we can remove these contaminants. And the only way to do that is to observe at many, many frequencies and use the different scaling of the CMB as a black body spectrum with the other sources. And so we occupy all of the available atmospheric windows and possibly split them as well, particularly for the SAACCs where we're going after the inflationary signal because it's so faint and so prone to contamination. So that then directs us to the sites, and this same sort of picture that Simone showed, you can identify the best sites to look from: the South Pole, the Atacama, the Himalayan Plateau, and Greenland. The South Pole and the Chilean Atacama are the best sites, and the US community has been working at both of those sites for a long time. And one of the great things for CMBS4 is that means there's a lot of infrastructure and experience in place, particularly with the South Pole Observatory, the Simons Observatory, and SAACC Prime. The other nice thing about sort of having this blank slate to write, to just find the best experiment you can, is that we can use multiple sites, and that's unique for CMBS4. It'll be the first CMB experiment to use multiple sites, and that means we can use the best of both. And the biggest area between the sites is the types of surveys that they can support. And so, for example, you can see, obviously, in order to conduct a wide area survey, you can't do that from the South Pole. So the Atacama is the best place to do that. And you can see the kind of coverage we're anticipating from the Chile. We'll hit about 68–70% of the sky. On the other hand, if you want to do an ultra deep survey and really drill on a single patch of sky to go for the B modes, you can take advantage of the fact that you can always see the same sky from the South Pole. And there's just a contrast here between the kind of survey you can do with the SAACCs in Chile versus the South Pole. And it's that ability to drill deep on a single patch of sky that really gives us the opportunity to go after, to push the threshold for the detection of this B mode down to the level that we want to for the science case we're going for. As Simone described, we'll use two sizes of telescopes. In Chile, we'll use two 6-meter segmented mirror telescopes. So the current design is the same design as SAACC Prime and Simons Observatory. Potentially reusing those telescopes. We have the beginnings of discussions about that possibility with both experiments. I was talking about one of the issues being both the mirror size for high resolution, but also the mirror quality for the large angular scales. And it turns out one of the reasons why you can't, or it's been hard to do the B mode science, this large angular scale science with the very large telescopes, is because of the segmented mirrors, and you just bring in too many systematics. And so the idea is that for the South Pole telescope, which will be doing the delensing survey to put on top of the large angular scale small aperture telescope survey, we'll actually try. We're working on a telescope with a monolithic mirror, hoping that allows that telescope to actually push down into those low multiples, to those large angular scales, and contributes to both the sensitivity and the systematics control for that survey. So that's why that's a different kind of telescope there, slightly smaller, but with a monolithic mirror. And then the plan is to have 18 half-meter telescopes. The initial plan is to locate all of the South Pole because of that ability to drill very deep. But the possibility would be to relocate some of them to Chile. For example, if there were the hint of a detection, then being able to observe a different patch of the sky, being able to observe from different location and address different systematics could be a very valuable thing to be able to do. So we're keeping that sort of as an option in our back pockets. The detectors will be using a little more than 500,000 cryogenically cooled superconducting transition edge sensors. In the same way that Simone described, these are each pixel is detects 2 polarizations and is dichroic. So you get four signals per pixel. So 125,000 dual polarization dichroic pixels. And those pixels are then etched onto wafers. So there's about 500 wafers. So you can see one of the pixels in the top there, and then a wafer of pixels in the bottom. And we'll observe for 7 years for all the surveys. And so you can see the kinds of detector counts, and the more critical number obviously is detector years. And this is, as we were saying, you know, order of magnitude bigger than anything that's been done or is being planned to have been done by the time CMBS-4 goes on the sky. So our timeline is that we're hoping to, you know, we have a construction project. We are a DOE project now. We're hoping that Astro 2020 and federal budget permitting, well, the construction project will run through about 27. We'll have staggered deployment. We'll be deploying telescopes to both the South Pole and the Chilean Atacama. So obviously that's a complicated process. So we'll stagger that over 2 or 3 years. And then operations running from something like 29 to 36. And as I was noting, this is a very natural progression. So in the late teens, we've had these 4 single site, single aperture experiments: ACT, BICEP, Keck, Polar Bear, Simon's Ray, and South Pole Telescope. Those have now are in the process of merging into these single site dual aperture experiments. So the Simons Observatory, ACT and Polar Bear came together to define and build that. South Pole Observatory is a convergence of BICEP and BICEP Keck and SPT. And then the natural next step is that we go to a single dual site, dual aperture experiment that brings in all of the expertise and all of the people who from all of these experiments into this one Uber experiment. So now coming to more of the focus, that was sort of the general introduction of what the experiment is. But here, this is now an overview of the data management schematic. So we're taking data at 2 different sites, South Pole and Chile. In Chile, we just have the short-term storage, and then to transfer the data essentially in real time to the primary data center, which is anticipated to be NERSC. From the South Pole, currently there isn't sufficient bandwidth to transmit the data, so it's SneakerNet once a year, you know, carrying disks. But we also have a lot of we put computing on site to be able to do the map making and the transient detection on site and transfer the reduced data products to the US over the network on a daily basis. And then we do all the reductions and simulations, and we have the alerts. It was, you know, listening to LSST makes our alert problems or our alert challenge seem a little laughable. We're anticipating a few hundred alerts a year, so nothing like the kinds of challenges there. But the dominant source, the dominant data products here are going to be the frequency, the single frequency maps of the sky that then are analyzed to across this slew of science cases. So this is the current, the pre-conceptual design for the site. Doesn't include any reuse of SO site facilities or telescopes, which is something we're very definitely interested in doing and in discussions about. But you know, there is room on the site. We have to have a plan that you know doesn't assume that we can do that. So there's room on the site to put all the telescopes. So you can see the 2 large aperture telescopes would go here and here if we weren't using the Simons one here. And we have room for the SATs to go in if it turns out that it makes sense to move some of them from the pole to Chile. So in terms of the networking, once we've compressed the data, we have a data rate of 1.2 gigabits per second, so nothing too terrifying. So the plan is to do real-time data transfer to the US data center, plan to be at NERSC. We're actually also working with Fabric, and it's the one of the possibilities there that is very interesting to us is that the real-time analyses, and particularly the time-critical analyses to identify the transients and issue alerts, may be performed while the data are in transit to NERSC on Fabric nodes. And you know, Fabric is expanding into an international partnership, and we're definitely interested in in encouraging and supporting the introduction of fabric nodes into South America. It seems like that would be a very useful thing for many of us to have that kind of capability available. Like SO, we're scoping for a month of on-site storage, but in our case, it's 10 times bigger, so 400 terabytes. On the other hand, even with 10 gigabits per second available, that only means it takes 4 days to clear a month-long backlog. So if you had the unthinkable network outage for a month, we should be able to clear that within about 4 days if we can run full tilt. And obviously, as I say, we're building on all kinds of experience across a whole range of experiments going back many generations. But obviously the most closely related experiment to CMBS4 in Chile is Simon's Observatory. So we're working very closely with them to coordinate the site networking aspects. And Eli Dart of the ESNet, who Simone mentioned as having been one of the people working on the perf sonar tests, is the CMBS4 Atacama data movement lead, and so is very involved and engaged in that activity. That was what I had. Any questions?
Well, just to comment, Julian. Very, very interesting. There's a lot of activity going on in that one area, and it sounds like you've got the right set of partners to help you with your data movement challenges. So very nice.
Yeah, I would also mention that it is a very natural development. It's very collegial. It's very much building on previous experiments to the extent that actually the L2 lead for the site for both Simon's Observatory and CMBS4 is the same person as Cam Arnold. Maurizio is also involved in that. Obviously, is the other L2, but there are some enormous advantages in having common people working on this between the experiments.
Thank you very much. Thank you. Any other questions or comments for Julian? Okay. Next up is Rob Salina for NGVLA.
Hi, folks. Let me just get this shared. All right. Hopefully you can see my slides now. Like Julian, I'm also bandwidth challenged. I'm going to turn off my personal video. Yeah, so I appreciate the opportunity to tell you, give you a short update about the NGVLA project. We're currently in the conceptual design phase, progressing towards our system code ER, and we'll talk about that and an emphasis on the data transport layer, of course, given the interests of this group. So brief recap on NGVLA. In terms of the scientific frontier that the telescope is aiming at, it's thermal imaging at milliarc second resolution. And so comparing what you need for that science goal to the capabilities of the VLA today, you need roughly 10 times the sensitivity and about 100 times the resolution of that array. We want to extend the frequency range at the same time. So we're looking at 1.2 to 116 gigahertz coverage, extending from H1 to CO. And scientifically, this is really an instrument that bridges SK and ALMA capabilities. It's a proposal-driven pointed telescope aimed at doing deep single field observations, very small area mapping. So it's kind of a high frequency complement for deep follow-up observations to say detections that are made with the SKA, which is more geared towards large mapping and survey projects. The array is a North American project centered at the VLA site in the southwestern US. And similar to CMBS4, we're under evaluation as part of the Astro 2020 Decadal Survey, so we're looking forward to that process concluding this year. The most visible progress of the last year on the design has been in the antenna design. We had a reference design that we had worked on with our colleagues at the National Research Council of Canada, but we procured an additional 3 concepts working with the industry over the last year, and you can see those three concepts here. And then towards the end of the year, we released an RFP for the preliminary design, final design, and prototype of a single one of these antennas. And so we're currently establishing that contract, but we ended up with 4 effectively mostly compliant designs to our key requirements. So we've really been able to de-risk the antenna, as well as get a much better understanding now of the cost of it. And this contract now for the final design and prototype has become a key pacing item for the overall project schedule. So the main schedule for the project you can see here, with an emphasis on the design phase. Construction would follow. And Astro 2020 being kind of a gate that allows us to transition from the conceptual design development towards a preliminary design, proceeding in the final design and concluding in 2025, 2026. And that's what we put initially in the RFP timeline for the antenna. So these milestones generally align with that broader view. But based on some feedback from the National Science Foundation, as well as from senior management, we've actually tried to pull our schedule left. And so the contract we're about to sign has the following milestones. And so we're pulling the antenna PDR forward, we're pulling the site acceptance testing results appreciably forward as well. And so we're making sure that we align the full project schedule. So today, basically, we need to start developing the interfaces to the antenna. So any subsystem that interfaces with the antenna really needs to transition from conceptual design to preliminary design in parallel with that antenna effort. Because while we have preliminary ICDs in place today, those need to be fully defined interfaces by the time the antenna preliminary design review is held. And test electronics have to get delivered at the end of calendar year 23 to support the site acceptance testing. So system level milestones are shown here. We've come up with a detailed schedule to the system code ER, and this will be a single review with all the high level decisions made for the project and identification of all the key driving subsystem requirements. The preliminary design review for the system would follow in Q1 and be February of calendar year 23, and the subsystem PDRs thereafter. The system level PDR is really focused on the architectural definition and identification of all the interfaces. And so it precedes the subsystem PDRs. And the subsystem PDRs have a typical threshold where they're trying to demonstrate prototype ready design to those defined subsystem requirements. In terms of our construction schedule, it's roughly a 10-year effort, starting in 2025, going to full operations in 2035, first ops around 2028. So I'm going to show some figures on the data side that are quite alarming by today's standards, but do keep in mind that we're talking about most of this deployment really being on the scale of 2030. So overview of the facility concept, as I said, 1.2 to 116 gigahertz frequency coverage. It's a 6-band system spanning 2 dewars, and you can see the frequency plan in the table on the right. The array has 244 18-meter antennas split into a main array and a long baseline array. And then we also have 19 6-meter antennas that capture wider field of view effectively, concurrent with the main array. So similar sort of breakdown to ALMA, but extending to much longer baselines in this sense. These are all offset Gregorian antennas, and they're all at fixed locations, so there's no reconfiguration capability in NGVLA. When we look at the main array, this is the reference design array configuration version C, shown here on these slides, and the shown previously at last year's meeting. The core of the array and the planes, so these are the figures shown on the bottom panel, those are proving to be very stable. We keep testing alternatives we might want to consider for the conceptual design review, and we're not finding significant gains. The mid baselines, which are the extended baselines that are outside of kind of a 30-kilometer or 36-kilometer radius, those are subject to some degree of optimization. So we've been looking mostly at scientific performance improvements that could be achieved with a more randomized set of arms that extend into Arizona and deeper into Mexico. And you can see that on the figure of the left versus the current technical baseline shown on the right. I want to emphasize that today, the effort has been mostly based on scientific performance. And so the baseline did consider the availability of roads, fiber, electrical infrastructure. The new design that's under work for these mid-baseline sites does not. And that's the next stage. So now that we have a better sense of the scientific improvements that are achievable, we're looking at the practicalities again, and we'll reconcile those two. On the long baseline side, this is the reference design, again, just a point of reference. And there is a key change here. We're going to eliminate the Westford site up in Massachusetts and instead have our 3-element LBA site at Greenback Observatory, the green dot. And that's based on the spatial coverage of the array is improved with that relocation, and it's a no-cost change. The other change that's in the works that is more speculative and may not be approved is moving 2 mid-baseline sites, possibly to a site in Florida and a site at the LMT, based on discussions with our Mexican colleagues and also, again, simulations of the array performance. But that's still definitely something that's purely, I would say, under consideration at this time, but is interesting, I think, in this group as we think about extending infrastructure further south as part of the project. I wanted to also highlight the Arecibo Observatory long baseline array site. So we've always planned for a long baseline array site at Arecibo, but more recently we've submitted proposals to the National Science Foundation to construct 1 to 8 of the 18-meter antennas at that site sooner rather than later. And these would be fully outfitted antennas with a complement of 1 to 34 gigahertz front ends and associated infrastructure. And these were joint proposals submitted with University of Puerto Rico, University of Central Florida, the Arecibo Observatory, and of course, the National Radio Astronomy Observatory. And I wanted to highlight them because one of those proposals includes a 100 gigabit link for the AO, I believe connected to I2. And so, again, relevant to the research infrastructure of interest of this group. I want to emphasize these are just one full proposal, a preliminary proposal so far. The larger one that includes the fiber link, if we invite it back for a full proposal, that would be due in September, and it would be an October 22 start for construction if those projects are funded. So something we'll keep an eye on, and hopefully I can have an update for next year. In terms of the data rates from the antennas to the correlator, the central signal processor at the center of the array, consistent with the goals of others in this group, we're trying to eliminate disks, and so we want to do real-time correlation of all 244 18-meter antennas. We're digitizing 20 gigahertz of bandwidth. A notable change since last year's update is that we've gone to 8-bit digitization at all bands. We've done a risk assessment for radio frequency interference over the life of the project. And there were concerns that we might need to go to more than 8 bits at low frequency, which say SKA has done as a point of reference. And we found we can live with 8 bits at low frequency, but there are some risks in band 6. And so we've moved from 4 bits to 8 bits in band 6. So all bands now are 8-bit digitization. We also want to eliminate requantization for the direct fibered antennas. And so considering the oversampling factors, this equates to 723 gigabits per second per antenna. So we would need 800 gigabit links. And this would only be true on our own infrastructure. So NGVLA installed fiber within the 300 kilometers of the array center, and I'll show you a map of that in a minute. We would requantize and be formatting for transmission on packet switched networks, and we include the data buffers and packet reordering hardware to accommodate that. And we'd still, though, like to have a fairly ambitious goal of about a terabit link per long baseline array site. So that's 3 antennas served by that terabit link. But the architecture is fundamentally flexible. So if that proves to be financially infeasible by the mid-2030s, we can always do less. We have the digital backend to scale our either bit rate or bandwidth, transmitted bandwidth, according to the practicalities of available networks at each site. So focusing again on the antennas that are closer to the VLA site, we think 196 of those 244 18-meter antennas can actually be directly fibered. And this would be new fiber infrastructure, primarily using existing right-of-ways shown in red on this figure. And the circle in green is 300 kilometers in radius. Beyond that area, we would rely on ISP connected elements. And these could be least fiber, least spectrum, or least bandwidth. And as I said, we'd be prepared for any one of those three, including the least bandwidth scenario. And the same is true for the long baseline array sites extending into the Caribbean, the Pacific out by Hawaii, and also into Canada and Mexico. Looking at integration with other facilities, there is one scenario where we still rely on disks, and that's VLBI recording capabilities to interface with other global arrays. And so we can record multiple beams in a VDIF format to whatever the latest MARC recorder standard will be. The array's preferred option, though, is to do the eVLBI. And so although we have 263 total antennas between the 18 meters and the 6 meters, we're actually designing a 270 element correlator. And the data buffers are deep enough that we could interface with in real time to other facilities. So this could possibly include real-time links to GBT, the LNT, phase ALMA, or others, depending upon interest of those sites for high-resolution observations, things like possible support for EHT-like projects. Data processing needs haven't changed. We're still projecting an average of 8 gigabytes per second and a peak of 128 gigabytes per second coming out of the correlator. So those are indicative of the data rates for our low-level products. The computing, no change here either, so 60 petaflop per second system, and that includes all the relevant efficiency factors for the massive parallelization that will be required for the data processing system. And this is all based on a set of reference observing projects that allow us to delve in deeply and understand the compute requirements for each use case and their relevant time allocations. Serving data to users because of the large data processing requirements is based on a science-ready data products model, meaning that we'll process the data in place for most PIs. So they will not be transferring low-level data to their host institution. Instead, they'll be interacting with an observatory-run pipeline to generate the higher-level data products, such as calibrated image cubes, that they would then use data analysis tools to complete their science projects. We do expect a degree of archive reprocessing and having associated interfaces for users. And this is really where the change has come since last year. We'd taken a very North American-centric view of the project initially going into Astro 2020, realizing that we needed to secure the support of the domestic astronomy community before we could really court international partners. But now that that's progressed much more, we're getting feedback from potential partners, and we're really going to go to a more distributed archive and reprocessing model, much more ALMA-like effectively, where there'd be individual science centers run by the partner institutions. And so it's a familiar model that we know we do have experience with, but that'll impact the archive architecture a little bit and the reprocessing capacity distribution. And so I think one of my things I really appreciate coming to this meeting is a reminder of how ambitious and hard some of what we want to do is. And NGVLA is really going to require a significant investment in new fiber optic infrastructure in the Southwest US with connections across North America. And this isn't something we want to go alone on, right? This is an area where we think collaboration there's many opportunities for that. And we certainly want to explore those fully. And for projects that are in later stages in the life cycle, we're certainly interested in hearing your lessons learned as well. So thank you for your time today. And with that, I think we'll take your questions.
Hi, Rob. This is Eduardo Toro from Knowledge Lab. In terms of the radio frequency interference, what are the expectations from this project and others respect of the satellites or transmissions or any other source of interference that could affect the functionality of this kind of equipment?
No, it's a great question. It's a key risk that I was worried about personally about a year ago. And so we've actually started some detailed studies to try and understand the evolving RFI environment, and in particular, the impact of the low Earth orbit satellite constellations. I'm quite pleased actually with what we found. this all needs to be proved empirically, and we've not published the memos until we can do so with the VLA and confirm that the model, when scaled to the VLA, is validated. But what we're seeing is that the fact that these objects move so fast, right? They traverse from the local horizon to the local horizon again in something like 19 minutes and 40 seconds. And that's in their higher orbits, never mind their lower orbits. So what this means is you get a lot of fringe washing. So it's a feature of an interferometer that you can suppress signals, a number of unwanted signals that are not near your phase center. And so a moving source, or a source that's moving relative to where you're looking, can give you a lot of natural suppression that you don't get with a single dish. And initial estimates are actually that natural suppression will protect about 96% of our observing time. So we will still lose spectrum at times, and we will still saturate the antenna if a satellite is traversing the main beam. But the threat area here actually is smaller than it first appeared, which was really nice to see. But yeah, we'll be conducting some additional tests with the VLA. We've already started taking some initial data. Starlink just started operating over our latitude. So this is an evolving space, but I think something we have to be mindful of, something we've incorporated data reduction and RFI excision steps in our data reduction system for, but we think it's a manageable risk. That's the key takeaway.
Thank you, Rob.
Thank you.
Any other questions or comments for Rob? Rob, I have a few for you. First, let me just say that the data rates that you reported and data movement requirements are quite challenging for the R&D networks, and I would like to suggest that we start to talk and start planning with you in some of the states that you showed, and also international sites. Did your survey identify that there's already existing fiber optic infrastructure, or it's going to be needed?
Yeah, within our survey of the fiber infrastructure is primarily focused on New Mexico and what we consider the main array today. So New Mexico and into West Texas in particular. We have not looked closely within the project team at the long baseline array sites. So David, is there anything you'd like to add about that based on
the it's of course there's not that many of them, tens as opposed to hundreds. And the big question is, how do you do that? And the answer is you get enough lambdas, and you have a tolerance of more than a millisecond for when the packets arrive. But the idea of packet shaping, are we going to be doing RF over fiber? Well, clearly, if you've got the fiber and it's in the core, that's an option. As soon as you go past that 30, 40 kilometer, you're going to be framing. You're using standard infrastructure from an ISP. You're looking for 80 lambdas. Clearly, fiber optic can carry this amount of data. You have a dark fiber and IRU, and you can do this. You may need to regenerate, but clearly the further, longer baseline sites are the real challenge. The fact that some of them are on an island doesn't help. So very much Arecibo, St. Croix, using those as springboards is, as you say, Julio, a huge opportunity to learn by doing for something that exists now.
Well, from what I was seeing in the maps, in the states I identified, there are research and education networks there that I'm sure would be available to start planning with you for your timeline. Internet 2 has also a presence there, ESNet as well, I believe, in some sites. So there's definitely resources available from the research and education networks to partner with you there. And also you mentioned the islands. University or the Hawaii is certainly well connected, as you know, David. And we're already talking about St. Croix. And as I've mentioned to you before, and it's very interesting that Rob mentioned a proposal submitted to NSF for a 100 gigabit link to Puerto Rico. There currently is an available 100 gigabit link between San Juan and Miami for research and education. It's part of the AmLite backbone that can certainly be used as well for what you have in mind. So keep that in mind, Rob. There's quite a bit of resources available that would be great to start to plan with you on your project. We certainly are interested in working with you.
You know, the construction of an interferometer, it's years and years, but every dish you add, you can plug it in and learn. Also, the fact that we're effectively integrating the VLBA into the NGVLA, clearly, you know, the sooner we start, the sooner we learn. And as I say, the further you are away, the harder it gets. I have some questions that I'll leave to the end about packet framing, the future, you know, the general knowledge around as fast as possible, but reliability doesn't matter, as opposed to every byte counts. So I'll ask those at the end, but definitely this project is a challenge for communications to have the understatement of the year. And it's limited by.
Well, yeah, Rob, I hope you'll be able to join us tomorrow, because you'll hear presentations from ESNet and Internet 2 and others that I think will give you insights as to what will be available to you.
Looking forward to it.
Just to follow up on that, Julio, this is Eli Dart from ESNet. I don't know what I'm sorry, I didn't catch the timeline for fiber construction, but I think we would at least like to squint at that and see if we have needs in that space. I don't know whether we have needs in that space or not, but anytime someone's doing fiber, you know, R&E fiber builds in the Southwest, you know, the stone soup networking is totally a thing, right? It's how a lot of us get a lot of things done.
And Eli, I would just quickly comment, huge appreciation to Los Alamos for lighting up the VLBA site there in the last year during COVID. So 10 gigabits clean, very stable, very nice. You know, that's what we need.
Okay, great. All right, we're a little bit behind schedule, but this is all really very interesting, excellent information to share. So our next speaker is Carrie Hayworth for NGEHT. Carrie, you ready?
Well, I was ready, and then my was I sharing before?
Don't know. Let's see. Are you?
Yeah, we saw your PowerPoint
presentation. Wait, did it come up? Okay, because I have two screens, and sometimes they behave, sometimes they don't.
There you go.
Yeah, it's up for you. Okay. Give it a second. Clearly, still up.
Yes.
Okay. Thank you very much. So I am here representing the Next Generation Event Horizon Telescope, and I really appreciate the invitation. So the project office, I put them on the page. Shep Dolman is the PI on this, and there's a big and growing NGHT team working on this. And so just to start with the background, this is the picture from now 2 years ago, if you can believe it, that was presented to the world of a black hole. And there's the part of it that's how we went from 10 arc seconds to micro arc seconds in order to have this resolution. And so I don't really need to explain to this group how VLBI works, but I will make the point that, or a couple points here, that we actually really need to be on opposite sides of the Earth, because to resolve M87, which is one of our two primary targets, we need that size telescope. And so we are all over the world, but especially on opposite ends. And our data is taken, you know, all of it's taken, and I'll talk about actual data rates later, but and then correlated at a central site. And so again, our observations of, that was presented in 2017, or that ran in 2017, was presented in 2019. Here were the 8 stations that participate in the observation. The way our campaigns run is they are 10 days long, and then 5 days actually trigger on the good weather. In this case, the weather was fantastic, which is why we got detections to all 8 participating telescopes, and it shows the baselines that we were able to get on the UV plane there. And you can see both Apex or Atacama and ALMA are both key members of this. So what's next? Well, for science-wise, we want to test GR to greater precision. Oh, that's a lot slower than it was. We're looking at the photon rings. We want to understand better jet accretion with the M87. And also for Sagittarius A star, we want to actually be able to explore the time variability a little bit better. And what you're seeing on the right there is my personal favorite, which is, we made a picture, we now want to make movies. And this is incredibly exciting to me. I am ready for a black hole movie. But as you can imagine, we're going to need bigger, better, faster technology. And so we are expanding sites. We are increasing bandwidth. We are building in autonomy, because you can't have these increased sites without a lot better autonomy than we have right now. And then we also are looking for faster time to science. And this is where I'm really anxious to be part of this group, because that really, it does make a difference as to how quickly we can get the data back. And we have major challenges there. So first of all, the expanded sites. So in blue, you'll see the 2021 array. And then all these red sites are sites that we're considering for expansion. So quite a few of them in South America are being considered. And in fact, all over the world, these are being considered for, their weather capabilities, their facilities, and also their baselines to existing telescopes. And then another really important concept in this, and why we can use kind of new sites, not even sites that have already been developed, but brand new sites, is that if we are able to anchor to a heavy hitter station, so for instance, ALMA, then we could actually put small dishes. So extend these 10 dishes into 10 small dishes. And so we're thinking between 6 and 10 meters. Right now, you can see the target is being 6. And by anchoring to these sites, we can still achieve the sensitivity we want, and also not have to pay the cost of 50-meter dishes all over the world. 6-meter dishes are easier to transport and certainly a lot cheaper to put up. This is a little bit of a detailed chart, but there's 2 really big important pieces of information on this chart for this group, and that is that, so we are increasing the bandwidth that we had before by 4. And what that ends up being once we do quantization is 256 gigabits per second. And so, that's incredibly fast. We're having a hard time just finding, a recorder that can do that. So we're building one up based on COTS components. But that 256 gigabits per second, based on a 5-day campaign and a 12-hour night at 25% duty cycle, and you get 1.7 petabytes per campaign. So that's kind of the challenge right there that I'm putting out right now, is that, we dream about real-time data transfer. We dream about being able to correlate real time and just be putting out the image while we're actually campaigning. We talk probably more realistically about, well, what if we could just get a little bit of data from each site while the campaign is going, and do some troubleshooting or some analysis on how it's going with that. And so, in that case, we're talking about 1 or 2 gigabits per second, and not that 256 gigabits per second. But I would sure love to hear somebody go, oh yeah, we'll be doing that in 3 years. So here's the kind of look at the way that our system works right now. So as I said, all over the world, the data is being recorded, and it said we're going to have 1.7 petabytes of data. Right now, it's gone, it's retrieved, it's put on a plane, and it's shipped to a central location for correlation and aggregation. And so these central locations, there's one in Bonn and there's one in Haystack. after that, and you can see on the bottom here, it shows the, what the reduction of data is in each point. So we start out with 80 petabytes, and this is kind of the analysis saying from all of the new sites, how many petabytes it's going to be. The correlated data will be down to 160 terabytes. Then further calibration, 160 megabytes, and finally the model reconstruction around 1 megabyte. So there's quite a bit of data reduction here. But there's that big challenge of how do we get it from the, all the sites, and in fact, some of our new sites will be places that don't have fiber infrastructure, and how do we get it to a central location? And I'll also mention here, and I'm going to mention later as well, that we're also looking into quite a bit of cloud correlation, because this is something that we can absolutely parallelize and take advantage of working in the cloud. There's still the same problem of how do we get it there. And so, you'll see on this, we have SSD ? And electronic transfer ? Because these are things we're exploring. And I liked the stone soup sort of analogy, just because I feel like that's what it's going to have to be. We're not going to be able to apply the same thing to every telescope. So, right now, what we're using is the Mark 6 for data recording. First of all, it has to be high bandwidth, and right now we're getting 32 gigabits per second onto it. And then it's archived for months. This obviously is a problem because we have to put the disks back out in the system. And so, the scientists might not be done with them. And yet we have to kind of pull them out of their hands and say, hey, we've got to get them back out so we can do another observation. Portability is a key. But once again, I'm talking about basically carrying these things. We would certainly like to have a better way. Even if it is we have a full recorder on site, but can pull off the data more slowly, after, over a period of time. Certainly with the South Pole, I think it takes us between 6 and 9 months to get the data. So something better than that would be absolutely fantastic. And so we're looking at SSD storage, which, is certainly coming down in price. We're looking at places that do have ground fiber. We haven't done a full analysis yet. SAACC is working on that. And then we're also looking into things like Starlink as a kind of a commercial commodity, and free space optical. We've even been talking to NASA. There's 100 gigabit per second where you just really can't put, or it's prohibitively expensive to put a fiber network in. That potentially we could, rent some space on a free space optical system. If you can do 100 gigabits per second, maybe we can get data down quickly. At the bottom here, I'm pointing out that this will likely be a staged approach. We're going to be exploring a lot of these things, e-transfer in parallel to building up a recording system and do it the way we've always done it. So here's our looking forward timeline. So phase 1, and that's where we're in right now, we are in the middle of designing. And so a lot of these ideas are coming out now of what can we do. Phase 2 will be building out and commissioning. That will start in 2024 and complete in 2030. So we should be on sky in 2030, looking to make our movies. So new stations that we're looking at are 10 small aperture dishes. Looking towards 6 meters, but possibly 10 meters at optimized locations. And I showed you the map of that before. The bandwidth expansion, that's a big one, 256 gigabits per second, which ends up being 1 to 0.7 petabytes per observation. We've got these data volumes between 10 and 100 petabytes. There's a lot of different kind of analyses there. They're trying not to limit right now. And then in general, we are looking for cloud correlation as well. So the estimated cost of the construction of these new sites, we're looking at $140 million, and then operation would be $13 million a year. And so, as I said, we are in the design phase now, and we are bringing together a lot of scientists to come upon to a consensus for what the science driver should be. And we have had a meeting that had over 500 participants. This was this past February. Obviously a virtual meeting, but there was a whole day of group brainstorming in which they came up with all sorts of science concepts and went off to simulate and model and kind of hone in on exactly what they want. And so finally, just the international work on the NGHT is underway. This is going to be just absolutely visionary. I am astounded just by the idea of black hole movies. Shep always says we're looking for executive producers, which means, you know, we are always looking for collaborators in this. We are committed to an inclusive program. We are really trying to make sure that there's an opportunity for early career researchers to get in early and be able to get sizable chunks of responsibility here. And we have, as I said, a target of late 2024, which is the final design and the proposals for construction, and then the whole completion would be 2030. And just like with EHT, we anticipate that 50% of the construction costs will be from non-US international contributions. And with that, I will conclude and see if there's any questions. I know I went through that fairly quickly. I was trying to make up some time.
Thank you for that excellent presentation, Carrie. Any questions or comments for Carrie?
I'd like to just welcome her to the SAACC because I'm very happy that she's able to present today, and also to listen and some of the other presentations of what's going on. It seems like it's a good fit.
Yeah, no, absolutely. And I just was really disappointed that I didn't get to join until this afternoon, but just hearing the last three really helped out a lot. And I'm glad that you're recording it so I can go back and review.
Carrie, will you be joining us tomorrow as well?
I will be joining for, there will be pockets. And I'm going to join as much as I possibly can, because I know there's a lot of good information there. And yeah.
Yes, I don't know how familiar you are with the research and education networking community, but we would certainly like to start to have further discussions with you and your team. Is there anything that we could do at this time to help you with your planning?
You know, it would be, as I said, we really do need help with the identifying what kind of capabilities are there. You know, what is the roadmap? And I'm sure that's, you know, something that you're going to be discussing tomorrow. And what I want to see is what the, you know, what can we rely on? And because okay, one of the things that I worry about is, you know, we talk about, okay, well, we'd like to do some real-time correlation. Maybe even if it's not with all 256 gigabits per data, it's with some subset of the data. And we sit down and start to discuss, well, you know, is that possible, and what could we do, and how much data would we need? And we really don't know the parameters as well. How much data could we get, you know, realistically? Is 10 gigabits per second realistic, or really is it 500 megabits per second that's realistic? Obviously, it's dependent on sites. Each site's got its own capability. And so certainly I think that having this discussion would help a lot. I am very new to this, to this community. So how, you know, I would ask you again, how you think you could help based on what our requirements are and what we're stuck on.
Yes, absolutely. We'd be very interested in starting a conversation with you. Just so that you know, we actually did start a conversation with EHT last year. We've been working with Vincent Fish and other scientists there, and we actually do have some trials going on right now with the antennas in Europe. There's one in France and another one, I think, in England. That
I thought, doesn't Iram have? Is that one of them? I thought that they had some.
I'm not sure, but I mean, those were the easiest ones to start with. So we hope to have some results to share with a broader community, but maybe some of that information would be useful for you as well. And there's just a lot of work still to do to help the EHT start to move more towards using research networks instead of shipping disks, which is has been part of your culture for some time.
Yeah, it certainly has, and it's because so one of the problems that we have is that because we only campaign once a year, the initiatives to say, well, you know, we all at the end of a campaign, oh gosh, you know, we can't do this disk thing again. We've got to get better. We've got to come up with all these new ideas. but we've got a whole year before the next campaign, and so a lot of times things lose momentum. And I do know that Vincent is working on this, because I've been on several of the emails where he's going and actually getting some doing a survey of the sites that at least that we have now for EHT. And then we're going to have to do it for the rest of the sites. But I certainly, and I know everybody really wants to get away from carrying discs around. I mean, there's several problems with it. There's many problems with it. So any way to get away with that would be helpful. And I see there's a question.
Yeah, somebody raised a hand here.
Nigel Sharp, please.
Just me. I just wanted to say, since I'm the program officer at NSF for both our involvement in EHT and our involvement in NG-EHT, we're very keen to promote not having to ship disks around. We're very keen to get more networking and get this. And we have a number of high performance networking initiatives, as Julio knows, and as Kevin Thompson knows. I can't see if Kevin's still on, that we hope will move that way. Yeah, Kevin's still there. I just wanted to say, please.
Yes.
I think we all agree, and I think that also just the idea of doing things on the cloud rather than a central site would be helpful. And we have a software engineer right now that is working on just that. Like, how do we convert everything that we do to the cloud? But
well, I should say you should be aware of security implications in the cloud, but I expect he is.
Yeah, no, there certainly are, and there's pros and cons to it. But I will say that if we do that, then that really takes away the whole idea of carrying around disks by hand.
Well, if you have the connectivity from all the data collection sites to the cloud, I mean, and that's the networking. I mean, in a sense, it doesn't really matter if you're putting it in the cloud or putting it on private disks, as long as it's the network that brings it together from the remote sites.
Yeah, and I don't think I do not think that we will ever get away from having a full campaign's worth of recorders on site, because I don't think that you can ever really rely on a network to without any kind of hiccups send out 256 gigabits per second.
Surely you've been on all these completely reliable Zoom calls.
I know, it's amazing how actually good it is, given what we do to this thing. But yeah, no, I would say that I just don't think that we'll ever hit that. But at the same time, hitting a piece of it, and then just having on, rather than having to go retrieve our disks, just have another plug-in where we can, get data off at some rate. There's really no requirement to have it overnight, obviously, or we wouldn't be able to make much.
Well, I don't predict ever, because I go back to when we took data on photographic plates. So.
Well, we've come a long way, so maybe that's a point of that we are going to make it.
Well, yeah, I mean, we got rid of tape drives at a lot of our telescopes because we just weren't recording enough at that point, and the networks were better. Now we're back to the point where the data volumes are beyond the networks or beyond the most widely deployed networks, but we're moving forward with that too. So,
yeah.
Do we have another hand up here?
Eli Dart.
Hey,
probably me. I have to put mine down.
Great talk. Thank you. Just to put in a plug for networks, I'm glad you're moving towards them. I would say two things. One is there's no substitute for seat time, and so the more you can get operational experience with using networking as just part of the scientific instrument that you drive, the better you'll be able to reason about what works for you and what doesn't. The other thing I will say is that the LHC experiments were very pessimistic at the beginning about the ability of networks to support them. And they ended up completely re-architecting their data model because the networks ended up being the most reliable piece of cyber infrastructure they had. So encourage you to do as you're already saying you're planning to do, which is to make greater use of them and see how that unfolds for you.
Yeah, but you know, it's a good point that, you know, that you can be very pessimistic, and then, you know, then commercial technologies kind of blows you away. And so planning on that and putting that in our operational model, I think is just a really important thing to do at this time. You know, as in we expect that this is going to be part of our system. We have, you know, actual software engineers that are working on networking and how we would interface for monitor control and things like that, who are, you know, they're taking a bigger look at it than scientists have done in the past, because they have more experience with it.
David, I just wanted to share an amusing anecdote for the VLBA. When we got a couple of sites out of the 10 with enough bandwidth, only 10 gigabits, to transmit the data in real time, we actually had them transmit it and then recorded onto the disk packs at the correlation site. And then they just sat there until the next day when FedEx arrived with the other 8 sets of disk packs. So you can kind of do this gradually because there is no real-time requirement. And you know, the important thing about an interferometer is it's useless until it's all in the same place, and nothing's ever equal. So the idea that you actually write this to the disk packs at the remote end, and then your processors still work. So you pick 1 or 2 sites, or 3 or 4 sites. So we've got to acknowledge the hybrid approach. And if you wait for every single site to be perfect, that will stall out.
No, and that's actually true, which is why the operational model sort of needs to be able to say, okay, well, we'll take a certain number of sites, you know, the ones that actually have this capability, and you know, work with those, knowing that we'll never get all of them, because it is going to be a major hybrid approach.
We have another question from Joshua Hoblet.
Yes, well, it's more of a comment, and that is, if you're seriously considering the cloud approach, it might be worthwhile trying to build a relationship with a cloud provider now and trying to understand what the costs are going to be like. So I just did a quick estimate on AWS S3 today. If you wanted to store 80 petabytes, you're looking at about $2 million a year just to store it on AWS at today's pricing. And AWS is actually a bit cheaper than most of the others. So there are significant costs related to storage in the cloud. And it's often one of the largest expenses, because you can spin up on demand a lot of other resources and then release them, but you have to hold on to your data, or you have to ship it out and back in again. And so I would just encourage you to start working on those relationships now to try and get a handle on what your IT infrastructure costs are going to be.
Yeah, we have started looking at that, and I'm certainly aware of the expense, and especially because scientists do not like erasing their data in any way, you know. So we could say, well, you only need it on until you're done correlating. So and that can actually be incredibly quick, but that's not how people like to see it, right? They want it there for a long time, and you know, we have to argue just to get it out of their hands back on site, and this is years later. So that is something that that we are going to have to show this price tag, and it might actually be something that people are just incredibly uncomfortable with, and it's going to kind of push them back into this, well, we're just going to keep disks, you know, and move around our disks, and I hope that doesn't happen. We have to realize that, you know, the data, the petabytes, 100 petabytes of data has a lifetime.
Yeah, we've been working with NASA to try to persuade the cloud providers to introduce sort of academic pricing or something, but there's really no incentive for them to do that.
No, there's really not. It's actually we you know, Shep because of the black hole picture does have a lot of clout where he can go and talk to people and say, what do you have for me, and how can you help me out here? And I will tell you that yes, they don't have a whole lot of incentive, because they just don't need to. If they like you, they may do it, but then again, they may not. And if you start to rely on it too much, you know, if they say, okay, well, we do like you, you know, let's give you a big discount, you know, and you start to rely on that and don't put in your operational model that you are not going to be doing that in the future, then yeah, the next year they can hit you with that $2 million price tag. And
yeah, we have plenty of past horror stories about these things.
Yeah, yeah. So I will say that I don't plan on relying on the goodwill of any company in order to give us a discount from that $2 million. It wouldn't be enough.
I was just going to say the cost of actually building an S3 equivalent. I mean, if S3 is replicated across multiple sites, there's all this reliability stuff built into it. If you really get into the nitty gritty of trying to build a system like that, not even counting software development, it's really not that far off on reality. So I don't think I don't think there's going to be a factor of 2 possible price discounting in there. I just don't think that's possible.
I realize that I have taken far over my 20 minutes time, so
it's okay. This is part of the open discussion. It's no longer just.
Well, let me stop my screen so it doesn't look like I am.
I was just going to ask you to do that, Carrie. That's great.
Yeah.
Well, it was a fabulous presentation for today. You know, we had a lot of conversation around it. So, Julio, do you have any other items?
Well, I just want to say the same, that it's been an excellent first day of presentations and discussions. We have a lot as research and education network operators to digest. And tomorrow it's our turn to present to you all. So I hope that you all will come back and hear what we have to report on updates since last year. I think there's some amazing opportunities to really start to plan with you and see how we can help you achieve your goals in the most effective way, and for you to leverage resources that are already in operation in many parts of the world that you're planning to do your experiments from. So Jeff or Bob, any closing remarks?
Excellent first day. In future meetings, we'll start off the observatories with a statement of, my name is so-and-so and I've been shipping discs for 10 years.
That's our new theme, is to no longer ship discs, away from discs. Bob, anything?
No, just to thank the speakers. It was a great day of presentations and discussion. It's so much exciting stuff happening in this area between the different science projects. So looking forward to hearing more and looking forward to seeing some of these things come online.
Great, thank you. Okay, well, we'll see you all tomorrow. Enjoy your evening or wherever you are. And we'll see you tomorrow, 11 a.m. Eastern time. Thank you.
Thank you.
Thank
Bye
you.
now.
Bye-bye.
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 Bye bye.